Try to start in time. Good morning. The people here obviously survived the banquet, but others might come somewhat later. The first talk of the session will be given by John Ellis, and he will talk about glimpses of SUSY, which give hope, but there's a question mark. Okay, please.
Okay, thank you. Ευχαριστώ. Kalimera. So, as I commented when I introduced the first speaker on the first day, hope springs eternal, and maybe experiment is giving two more reasons to continue hoping for supersymmetry, and I'm referring to the measurement of G-2 and the measurement of MW by the CDF collaboration. So probably you've all seen this picture before of the arrival at Fermilab of the magnet that was used previously by the Brookhaven experiment is now being used by the Fermilab experiment. So I'm not quite sure whether this is the dawn of a new era or the sunset of all our hopes. We'll come back to that in a moment.
It's the clouds that bother me.
So turns out that I write papers, usually with Dimitri, on G-2 about once every 20 years. So this is our first effort back in 1982, and this is another one that we wrote about 20 years later when the first Brookhaven result came out. So the sort of standard reference for the standard model calculation of G-2 is, of course, provided by this theory initiative review that appeared in 2020. So they gave a comprehensive review of all the QED calculations and also the hadronic uncertainties, in particular those associated with the hadronic vacuum polarization, this infamous diagram which you see down here. So here is just one plot taken from their paper. So you see here that the dominant contribution, hadronic contribution to G-2 comes from energies below about a GeV. The uncertainty in the calculation is sort of a half below 1 GeV, a half between 1 and 2 GeV. By contrast, high energy contribution is under good control from both experiment and QCD. So anyway, here's their estimate. The estimate of the hadronic vacuum polarization contribution has an uncertainty below the % level. Okay, so that gives us this discrepancy between their standard model calculation and the experimental average. It's encouraging to note that the Fermilab measurement agrees extremely well with the previous Brookhaven experiment. It's also encouraging that the statistical error, which is a larger part of this error bar, and so there's hope that as the Fermilab experiment gets more data, then we'll get greatly increased precision in at least the experimental measurement. Okay, so when the Fermilab result came out, there was a rush of papers, and for a month or so I tried to keep track, and I color-coded the papers according to the theoretical interpretation, and green is the color of hope, and as you can see here, there's a whole bunch of supersymmetry papers. Okay, let me just remind you briefly what are the key elements in this calculation at the one-loop level. So you've got diagrams which involve neutralinos and smuons, or charginos and neutrinos. If you're thinking about the neutralino-smuon diagram, you have to deal with the fact that there's actually 4 different neutralinos and there's 2 different smuons and they mix. And actually the most important contribution, generally speaking, is one which involves the mixing between the left and the right smuon. And we'll come back to that later on. Okay, so what can one do in supersymmetry? Well, of course, for a long time, the sort of default supersymmetric scenario was the CMSSM, where you assume universality of soft supersymmetry breaking at some high scale. And in that case, you're totally screwed. Basically because the smuon, here's the mass of the smuon right, has to be very large when you take into account all the constraints coming from the LHC. So this is actually largely based on a calculation that we did in 2017. We tried updating it in 2021, but we never actually quite succeeded. So this reference here is a little bit out of date, but never mind. Anyway, so the smuon is very heavy. The neutralino could be as light as a few hundred GeV, but because of the heavy smuon, you can only get a very small contribution to G-2 from the CMSSM. And the sort of standard theory calculation would require something way over here somewhere. And here you see for the first time the magic words BMW. And I'll come back to BMW a little bit later. So you may be wondering whether, with all the heroic efforts of the LHC experiments, some of which we heard about earlier on in this meeting, whether there is still scope to have a relatively light smuon and or neutralino. And so these are the latest plots that have been presented during the course of this meeting. So let's just look at the one on the right for the time being. So what you see here is that actually you could go down to, for the mass of the smuon, down to 100 GeV, or even a little bit less, where you get a constraint coming from an old Lhc experiment. Just one point I would like to make here. In most models, the selectron and the smuon are almost degenerate, but the right-handed smuon and the left-handed smuon may not be degenerate. And so the most relevant constraint of all these here in that class of model is the one on the right-handed selectron, because that's the one that should be degenerate with a lighter smuon. So over here on the left, in addition to reproducing the experimental constraints, they've also thoughtfully included some of the masses that could give you G-2 under various different hypotheses. So you can see that there is this channel which is allowed where you could indeed get, you could explain the discrepancy between the standard model calculation and the experimental measurement. As an example of this, this is from a paper that we actually did get out in 2017, where you see that you can accommodate the G-2 result. At that time, of course, it was just the Brookhaven result, but as I showed you, the Fermilab result is essentially identical. You would need a smuon, which weighed about 300 GeV or 400 GeV, and a neutralino, which is a little bit lighter. Absolutely no incompatibility with the LHC constraints, and a very big carrot dangled in front of our experimental friends to work just a little bit harder to try to explore this channel of low smuon and low neutralino masses. Okay, so here I just show a couple of plots that came out after the Brookhaven measurement from Sven and collaborators. And on the left, they show a scatter plot of chargino mass versus neutralino mass. On the right, it's lepton mass versus neutralino mass, a whole bunch of sample points in parameter space. The good ones are the ones here which are red stars, which fit G-2, get the right relic density, scatter all with direct dark matter scattering and all the LHC constraints. Okay, now, BMW. So here you see calculations based on measurements of the hadronic vacuum polarization. And here you see the Brookhaven measurement. As I said, the Fermilab measurement largely overlaps. Here you see a bunch of lattice calculations with relatively large error bars. And you see this one, BMW, small error bar, comparable with the hadronic vacuum polarization error bar, but a very different central value. And I'm not an expert on the lattice. I'm not going to go into it in detail. Here's just some plots on how they have to do some extrapolation. They've got very good lattice data, but they have to do some extrapolation. You have to understand the details and believe the details of that extrapolation. But anyway, if you do that, then you find that the discrepancy with the experiment is much reduced compared with the conventional hadron vacuum polarization calculation. Although, it's still off by, 1.5 sigma, but I don't think we care these days about 1.5 sigma. Okay. So my own personal work on this subject has been in the context of the flipped SU5 gut. So we saw in the CMSSM, which is basically akin to supersymmetric regular SU5, that you cannot explain G-2 with a phenomenological model where you allow the supersymmetric breaking masses to float basically any way you want, you can explain G-2. What happens if you tie just one hand behind your back and you have this flipped SU5 model, which has a few more parameters than the CMSSM or regular SU5? So you get extra parameters because you've got an additional U1 factor. So you've got two different gaugino masses, which frees up to some extent the mass of the neutralino. And the right-handed electron and muon are sitting in singlet representations of SU5. And so their soft supersymmetry breaking mass could be different from that of the other sleptons and squarks. So in this model, you could have small masses for the lightest neutralino and the lightest muon. And this shows you what we found when we did an analysis in flipped SU5. So here we've got the Lhc constraints. Here we've got the LEP lower limit. Up there, the lightest supersymmetric particle will be charged, so that's really bad karma. The yellow points are the ones where we get a relatively substantial contribution to G-2. So these are in the sort of vacant channel that we were looking at previously. And this is actually our best fit point. And I checked that best fit point is still compatible with the very latest Lhc constraints. So in this model, you can get halfway there, but not all the way. So this is the discrepancy with the data-driven hadronic vacuum polarization calculation. Here's a discrepancy with BMW. Here's the CMSM. Here's flipped SU5. Flipped SU5 could certainly accommodate BMW. And if you really, really, really try very hard, you can even get as far as the data-driven value. So, all very nice. But, for a year or so, I think people sort of waited to see whether the BMW lattice calculation will be confirmed by other lattice calculations. And the bad news is, yes, it has been confirmed. And so there was this paper by Che et al., which appeared, yes, it's still this month. And that's this little green point here, which basically coincides with the BMW calculation. And I should say it's not a complete calculation. What they do is a so-called window calculation where you look at some region of the integral contributing to G-2, where you think that the lattice is best equipped to provide an accurate calculation. And in that window, BMW is basically confirmed by Che et al. And if that wasn't bad enough, there was a conference recently in the US, the Schwinger Fest, where other lattice groups presented their results, and a lot of them also seem to be quite compatible with BMW, and not so compatible with RBC, which was the previous most accurate lattice calculation. So clearly there are issues here, like how do you reconcile these different calculations with relatively small error bars? But it could very well be that there is still an anomaly in the anomalous magnetic moment, but it may well be a smaller anomaly than what we thought when the Fermilab result came out. So just to finish off on this topic, this horrible table gives you the spectrum that we get in our best fit flipped SU5 model. And so this muon is light, the neutralino is light, so opportunities to look for them at the LHC. Other supersymmetric particles are heavy, and we get the right relic density right on the nose, basically without even trying. We didn't have to adjust parameters to get the right relic density. And that's a common feature that's been found in other calculations, that if you're in that channel, then you can easily get the right relic density. Okay. Now, MW. So this plot here compares the CDF measurement of MW with its stated errors, and it's confronted here with previous experimental measurements from LEP and the LHC, and also D0 measurement. And over here we have standard model calculations. So on the one hand, there's a 7.2 standard deviation discrepancy with the standard model value prediction. On the other hand, there's also quite some tension with the previous experimental measurements. So I think the tension with the other experimental measurements is also something that needs to be understood. Anyway, if you just average the previous measurements, that gives you this gray error bar here, then what you can do is naively combine that with CDF, and you get this black point here. Probably you shouldn't be so naive. Probably you should expand the error bars according to the PDG prescription when you've got mutually incompatible measurements. But it's not going to change very much what I'm going to be saying later on. Okay, so let's look a little bit more at the CDF measurement. So if you look down their table of uncertainties here, I've highlighted for you the principal uncertainties which one has to look at in order to assess whether one should take this measurement at face value. So just to remind you, the way you measure the mass of the W is you measure a lepton, and then you sort of go from that to the actual mass of the parent boson. So you need to have a good measurement of the lepton energy scale. That's one of the principal uncertainties. You also need to have a model for how the W is produced, and that is also one of the relatively large uncertainties. And the calculation is also dependent on the distribution of the partons inside your protons or your antiprotons that collide to make your W. And that actually is the largest of all these uncertainties, apart from the statistics. So there have been some questions about the accuracy of the muon momentum measurement. So I'm a theorist. I don't have any dog in this particular fight, but let me just show you a couple of plots. So the top one here is taken from the CDF paper, and the lower one is taken from, I confess, a blog by another experimentalist, Tommaso Dorigo. So what CDF did was they extrapolated these measurements here of things like the J psi and the upsilon down to down to lower values of GeV over PT of the muon, in other words, to larger values of the muon. So their direct measurement of the uncertainty coming from the measurement of the Z is not so accurate. So what Tommaso did was to say, well, you know, what we really are interested in these relatively high PT measurements, and if he fits those, then he gets a larger uncertainty in a different central value. So I'm sure that CDF has an answer to this, but I don't know what it is. So the next uncertainty was the modeling of the W and Z production. So for this, CDF used a code called ResBos, but they used a version of ResBos which is about 20 years old. I mean, they sort of fixed it up somewhat, but still, it's a relatively old code. So there's a new version of ResBos, which includes more higher order perturbative QCD calculations. And there are other QCD calculations that aren't included in ResBos version 2. So it would be nice if in the future the modeling of W and Z involved the latest QCD calculations. Now, in their paper, CDF looked at a relatively restricted range of parton distributions. Other people have looked at a larger selection of parton distribution functions, and they actually estimate a larger uncertainty than what is claimed by CDF in their paper. So all that is to say, I don't know. Some people say that the uncertainty in the CDF measurement might be significantly larger than what they claim, but I'm going to take it at face value for the rest of this talk. Not just me, 90 other groups of theorists have also taken it at face value, and hope springs eternal, so there's a bunch of supersymmetric interpretations as well. So initially, I'm not going to use supersymmetry. I'm going to use a very general approach, the standard model effective field theory, where you add in to the standard model calculation dimension 6 operators with coefficients, which you then constrain by a global fit to all the available data. And that, I think, is the most effective, efficient way to extract possible information about physics beyond the standard model. So here is a sort of catalog of all the dimension 6 operators that we include in our global fit. I'm not going to go through them in great detail. There's a few of them that could potentially contribute to MW, and I've highlighted them here. But you can't just put in whatever value you like for those operators, because they're also constrained by other data. Those operators contribute to electroweak precision observables, Higgs production, TT bar observables, and so on. So if you want to see how large a contribution you could get to MW from those dimension 6 operators, you have to do a global fit, and that's what we did. And here we confirm that if you do a global fit with a new value of MW, then each of those operators individually could make a significant contribution, and its coefficient is pulled away from 0. Whereas if you took the previous measurements of MW, there was no pull away from 0. Okay, now where might those operator coefficients come from? Well, they could come from the tree-level exchanges of massive particles. So we considered all possible single-field extensions of the standard model. Some of them are scalars, some of them are vectors, and the rest are fermions. Then we identified which of those could make this sort of tree-level contribution through the dimension 6 operator. And so a bunch of them could in principle. However, a bunch of them, instead of increasing MW, decrease MW. So you can cross those out. And here there are a few which would have the right sign and could potentially increase MW. And here are the sort of ranges of masses that you would need for those single field extensions if you assume that they have unit couplings to standard model particles. Probably they don't, but the estimate of the mass goes linearly with the magnitude of the coupling. So if you think, for example, the coupling is 0.3, then you would decrease the mass by a factor of 3. But we're talking about masses in the TeV range. So two of these possible single field extensions involve vector bosons. One involves an isotriplet scalar, and a couple involve singlet fermions, either a neutrino-like fermion or a selectron stroke smyon-like fermion. And some of these can be found in principle at the LHC, others look much more difficult. So, since I'm now on 0, what can one do with supersymmetry? So just before the measurement came out, there was a paper by Banyatsky et al., where they analyzed the possible contributions of light electroweak particles. And there's a cloud of possibilities here, which could take you up to the previous world average, but not to the new world average, and not to the Cdf measurement. But there could, in principle, also be a contribution from stops, which they did not include in that. And here is a previous calculation of the stop contribution. And if you put the two together, then you get that green arrow sitting on top of this electroweak smear here, and you could reach the new world average. So supersymmetry could make a significant contribution to MW, but not enough to explain the Cdf measurement by itself, but enough to explain the new world average. So, last slide. People often ask me, well, what lies beyond the standard model? So, I still say supersymmetry is the best scenario. You've got new motivations from LHC runs 1 and 2, and maybe G-2 and or MW is also providing us with a glimpse of supersymmetry. Thank you.
Okay, thank you very much for this nice talk and making sure that the title of the conference should stay what it is.
I believe these two topics are actually somewhat related, because when you believe that the vacuum polarization, hadronic vacuum polarization is bigger than previously thought, I believe this makes the discrepancy in MW somewhat bigger, isn't it? The standard model prediction of MW goes down a little bit if you increase the vacuum polarization to accommodate G-2 better.
Yeah, so there's been some analysis of that. I think Peter Athron and collaborators in particular came out with a paper shortly after the Cdf measurement making precisely this point. And I'm not going to argue that it's the same type of supersymmetry which could do both.
Could you go back to the Dirigo plot, please, John? Okay, so how much difference in the measured MW does this make, this different extrapolation?
Okay, so it would be a difference between 1.4 per mil and 1.3 per mil, so that's 1/10 of a per mil. So that's 10 to the minus 4. 10 to the minus 4 of that's like 8 MeV, something like that.
Okay, so not enough, but all these things seem to be about, all these effects, the PDF and so on, they all seem to be about 10-ish MeV, right?
Yeah, so I didn't explicitly comment. So there's been an analysis by experts in electroweak analyses who say that going from ResBos version 1 to ResBos version 2 is probably of the order of 10 or 15 MeV.
Thanks.
And that was also, coincidentally, the sort of order of magnitude of PDF uncertainty that was claimed in this paper here. And there have been other papers that I didn't have here, which also point to similar uncertainties coming from PDFs, but different aspects of the PDF fit. Carlos is being very patient. You've given up?
No. I'm waiting.
Hi, yeah, very nice talk. Actually, I have a question, but on that comment, I saw that paper and I wasn't sure if they included differences to the spin correlation effects. I saw there were next to leading order corrections, NNLO corrections, but maybe not the spin ones. So I don't know if that would have an important effect.
So you're talking about...
Yeah, for
Yeah,
response too. But okay, that wasn't my question. My question was I was very interested when you showed the for the WMAS, the EFT, the new operators that were relevant here but were constrained by other things, and it included TTV. And in general, we've seen that Atlas and CMS both measure a bit of an excess in TTW. Though, okay, the uncertainties aren't that large, and there was a nice talk by Victor yesterday on top measurements at CMS that showed maybe with the latest generators and corrections, they're getting a little closer. But have you studied those at all, or do you think those might be significant? And could these operators also contribute to excess TTW events?
Yeah. So we haven't done so yet. So this analysis that I just presented to you was largely based on the data set that we had in this paper that we wrote a year and a half ago. Okay. And we have it planned to do an update of that. I think we're waiting until we get all the iChip results, and then we'll throw everything in, and we'll see what the picture looks like. Carlos, you're itching. You're sort of hesitating.
No. I give you my right to ask the question. You want? Okay. So in the G-2, in one of your slides, you had the analysis made with the PMSSM 11. Has it been done for the full PMSSM?
Well, not in the way that we would like to do such an analysis, because the full PMSSM, you've got many more parameters, and to sample those parameters in a meaningful way, I think is computationally too much. It's just so maybe we could do the PMSSM 12, okay, but PMSSM 20, I don't think so. I mean, just think about it, right? I mean, if you want to sample, at the 10% level, each of the possible 20 values, right? That's 10 to the 20 points. Right? So, of course, you do smart sampling, so it's not really 10 to the 20, but it is a hell of a lot if you want to do it properly.
Thank you.
You have a question?
Okay.
I don't see any other questions, so thank you very much. If we move to the next speaker, there's a small change in the program. The two talks are switched, and we will have Sven Heinemeyer, who will be giving the next talk.
Good morning, and thanks for giving me the opportunity to talk about one of my favorite subjects, namely new Higgs bosons around the corner. And I said, well, the laser is the big one, I guess, yeah? Yeah. With SUSY and without SUSY, and we will see where we stand. I will talk about some hints that appeared at 400 GeV. I will talk at some hints that were there for quite some time at 95 GeV. And I hope to keep the tension here by naming the fourth topic here, the third axis at the same mass, which I think is very promising. To start with, we have discovered a standard model like Higgs boson. Standard model cannot be the ultimate theory. We are all aware of that. Only possible conclusion, the standard model, the Higgs that we've seen, can't be the Higgs of the standard model. This is impossible. But of course, the real question that we want to ask is, does the BSM physics that must exist has any relevant impact on the Higgs? Are there any hints from the LHC? And if so, which model may fit these? And the answer, how can we answer this? Of course, we can check for the changed properties of the Higgs discovered at 125 GeV. I'll not talk about this. I'll talk about the check for additional Higgs bosons, and I write here above and below 125 GeV. maybe I should say this before, when you think, everything below 125 GeV has been ruled out by LEP and by the LHC or so, this is clearly not true, and you will see where these points are lying. I will talk about two models where I will do the interpretation. First, the non-SUSY model, which is the next to 2x double model, the N2HDM, which has nearly the Higgs structure of the NMSSM. We have 2x doublets and one real singlet here. The Higgs potential. We have the normal Z2 symmetry that prevents the flavor change in neutral currents at tree level. And we have an additional Z2 symmetry that forbids some other terms, but it's broken by the VEF of the singlet. Important for us here are the physical states. We have 3 CP even ones, 1 CP odd, and the pair of charged. So with respect to the 2HDM, just 1 CP even Higgs boson more. As I said, we have the normal Z2 symmetry. We have these 4 types. I'll come back to this later. I assume that this is more or less known how this works. This works here exactly as in the 2HDM. And for the CP even Higgs bosons, we have to rotate to the physical basis. We have here this matrix that will appear later on, a 3x3 matrix governed by 3 mixing angles. And the physical input parameters that we are using are these 3 mixing angles, the usual tangent beta, the ratio of the 2 VEFs, the VEF of the standard model effectively, the VEF of the singlet, all the masses, and this parameter M12 squared that breaks softly the first Z2 symmetry. Now, the second model that I will talk about is then the NMSSM, or the Z3 invariant NMSSM. This here is the Higgs sector of the MSSM and the Higgs potential. And in the NMSSM, we add then here again this singlet. So it's similar to the previous model, but now it's a complex singlet. We get these additional terms. And I just listed here the input parameters of the Higgs sector. In the MSSM, we would have only the charged Higgs and 10 beta, and now we have here 4 more free parameters. Good. The Higgs spectrum, of course, again, 3 CP even ones, now 2 CP odd ones, the charge, the Goldstones, and the neutralino sector is extended by 1 singlino. I come to the axes at 400 GeV. Actually, I will talk about one axis at 400 GeV. When we wrote the paper, there were 2 axes. One has disappeared by now. This is the one that survives and is actually the nicer one, in my opinion. It appears in the CMS Higgs boson searches where they look at the decay to TT bar. So these are the diagrams that contribute. And the interference of signal and background gives you in this MTT distribution, gives you this kind of peak dip structure. And this is exactly what CMS observed here. And one can also put this into the plane of the A boson mass, if you think it's a CP odd Higgs boson, and this is the coupling constant of the A to TT bar. This is the expected limit that they hope to find with the 1 and 2 sigma uncertainties, and this is the observed limit. And you can see that here is this discrepancy, most prominently at 400 GeV. The local axis is 3.5 sigma, the global one is a little bit less than 2. And this was the hardest part of the project, to get this kind of chi-square contribution from CMS. It took us about a year. One can see here the chi-square contribution that one gets, depending on the coupling of the A to TT bar and depending on the width of the A boson. Yeah, and here there are this largest axis, and with respect to the standard model, which is here, we have a chi-square contribution of 14. In a moment, I will show you results where we not only look at this one, but of course we also have to fit the standard model like Higgs at 125 GeV. So the total chi-square will be composed out of these two. Yeah, the one from the 125 GeV Higgs, based on all the LHC rate measurements where we use our code Higgs signals, plus this one from the TT bar. So, question, can this axis be accommodated in the N2HDM? You can anticipate the answer already. We did a parameter scan. I'll not go into details here, just to show you that we tried to be extensive. And of course, we did include all the relevant constraints. I, again, will not go into details. Tree-level perturbativity, that the potential is really the minimum one or at least long-lived. All the Higgs searches, the properties, as I said, from this 125 GeV Higgs boson, flavor physics, and electric precision data. This is the result of our parameter scan. This is, again, the coupling A TT bar. This is tangent beta. And here we have several best fit values depending on the width of the A boson. These are the points. This is our best fit point. Main message, yes, indeed, the model can accommodate this axis relatively easily, as we will see, for low 10 beta. Yeah, here in this range, for low 10 beta, the agreement is quite good. So this works. I have a few more plots on this. If one puts it into this plot that CMS presented, we would live right here. I mean, 400 is chosen by hand, and then these are the points that we find, and you can see that this nicely explains the axis that they've seen. How can we test this scenario? For example, by measuring the couplings of the 105 GeV Higgs boson. Here I show the plane of the coupling of this 125 GeV Higgs boson to gauge bosons versus B quarks. The color scale shows us 10 beta, so look only at the dark points. Forget about the light points, they came from the other axis that I'll not discuss here. So these are the dark points. This here are the anticipated precision of the high-Lumi LHC, and the small ellipse here is if you add in the measurement of the Lhc 250, potential 250 GeV E plus E minus collider. And one can see that most points would give you a very large deviation, but of course the standard model, which is the center of these ellipses here, could also be realized and we wouldn't see anything. But most of the points that give you the axis are indeed, would indeed give you a large deviation. Same holds if you look here for the coupling to TT bar.
So the 2 Higgs level model is type 2?
Here, maybe I didn't say it, was on the slides. We focus right now on type 2. This is correct. Sorry. I should have said it. Yes, you're absolutely right. Next question. Can the model be accommodated, or can the axis be accommodated in the N2HDM? In the NMSSM, sorry. And we go to the alignment limit. Again, we do a parameter scan. This, of course, is the Higgs sector of our model. And yes, we found that also this model can do it, although not as nicely as the N2HDM. We have less freedom. While this is the N2HDM solution, this is the NMSSM solution. You may wonder, why do the points lie directly below this line here? This is accidental. Yeah, there's nothing to it. It's just what we found could be accommodated. Yeah? So we get smaller couplings of the CP Higgs boson to TT bar. But as one can see here, the chi-square contribution, chi-square TT bar, in the N2HDM it's effectively 0. Here we are at units of 5 to 6, whereas in the standard model we have 14. It's not a perfect fit, but it substantially improves the agreement with the experimental data. And why can't we go to higher values? The reason is the search for the charged Higgs bosons, which I saw on the right-hand side here. These are again our points, but there was no axis for the search of charged Higgs boson. In fact, they set a stronger limit than that expected. So here, this is the expected limit, and this is the observed limit, and our points live below. If they had gone to the expected limit, then we could also live here at higher values. On the other hand, this was the previous search from CMS for charged Higgs bosons. This is the current version, or the current result. And the improvement with more luminosity, this was here first year run 2, this is full run 2 data. The improvement was rather moderate, so they didn't go in the direction of excluding more than they expected. Therefore, I think this looks still very promising. Again, can we test this at future colliders? Yes. Again, we could look at the couplings of the 125 GeV Higgs bosons to gauge bosons and to BB bar. These are our points. High Lumi LHC will not be good enough. We need an E plus E minus machine, but the plus E minus machine would clearly see a strong deviation from the standard model. Good. I come to the axes at 95 GeV, and I will start with the axes that have been around for quite some time. This is our summary plot that shows the results for the searches for light Higgs bosons at the LHC. So PP going to Higgs, decaying to 2 photons. And I'll try to walk you through this plot where we summarize the results. This is the Higgs boson mass. This is the excluded cross-section normalized to the standard model. So this is the standard model line. Red is CMS, blue is Atlas. Dashed is the expected limit, and solid is the observed limit. So one can see the expected limit here goes up because here's the Z boson sitting. You have larger background, therefore the limits become weaker. And then this is flat. The observed limit from CMS, on the other hand, this is based on the first year run 2 plus the run 1 data, goes up as expected, goes down, and then has this peak here where actually the axis is sitting, and they get a mu value, so the ratio of production cross-section times branching ratio divided by the standard model expectation for Higgs at this mass, which is 0.6 plus minus 0.2, corresponding to a 3 sigma axis. Now, normally, the other experiment excludes this kind of hints for new Higgs bosons or BSM physics. Therefore, one has to look at ATLAS. And this is the ATLAS expectation. So they could cut into this region here. The ATLAS expectation is based on 18 inverse Hampton-Barnard 2 data, so more than twice as what CMS has been using, and still their sensitivity is much lower, which is because they have a worse control of the background. You can ask me all details later. What is ATLAS observing? As I said, they could cut into the preferred region. They see the Z peak here, and then they see this, I would say, shoulder-like structure, something like 1 sigma. They could exclude it partially, but they don't. Yeah? And how I like to phrase it, if there is something, it would look exactly like this. On the other hand, we know that the reverse doesn't hold. Yeah? If it looks like this, doesn't mean that there is something. Yeah? But if there is something, it would look exactly like this. Then for the more senior people among us, yeah, you remember the lab axis at 98 GeV, coming from the production in Higgs-Strahlung, the decay to BB bar. There's one axis at 98 GeV, but it's in the BB bar channel, so it's rather broad and also perfectly compatible with 95 GeV, where, so this is sitting here, where they observed this 2 sigma axis, the mu value 0.12 plus minus 0.06. And of course, since we have 2 axes at the same mass, the question is, can they be accommodated together in a model? So what do we need to fit this? Of course, we go to the N2HDM. We put one Higgs boson at 95 GeV. We put, of course, one Higgs boson at 120, so 95 and 125 GeV. In order to get the right rate for the lab axis, we have to reduce the couplings to gauge bosons. On the other hand, we have to get a large decay to photons. How do we do this? It's very difficult to get a larger decay by new particles in the loop. What you have to do is you have to reduce the main other decay channel, which is BB bar. So we need a reduced rate to BB bar to enhance the branching ratio to photons. On the other hand, the coupling to TT bar should not be reduced in order to accommodate this. What is more or less free still is the coupling to taus. It can be reduced or enhanced. Then one looks at these 4 types. This is this R matrix that I was mentioning before. And then there are these factors with sine beta. And if one says, for example, we need this reduced to enhance this, this can be done in the various models. But if one looks, well, if we want to reduce BB bar but not TT bar, this immediately rules out type 1 and type 3, yeah, because they go together. You can't suppress the one and not suppress the other. So type 2 and type 4 survive, and they differ by their couplings to taus. Yeah? They can be either enhanced or suppressed at the same time. So they can both do it, but it's nice that type 2, which corresponds to SUSY, as we know, is one of the candidates here. But as said, they can be distinguished via those couplings to taus. And if one does a parameter scan, this is the gamma-gamma mu value, this is the LEP, the BB bar mu value. These are the parameter points that we scan. This is the 1 sigma ellipse. We see many, many points here. The color coding tells you how well the 125 GeV Higgs boson fits to the LHC data. So dark colors are good. We see relatively dark colors also here. This is our best fit point, and it's clear that the two axes can be accommodated at the same time. The main challenge, or you may ask, which model can do the 2 axes, or the 2 masses together, the 400 GeV and the 95 GeV? And we tried this, of course. This is the result in the N2HDM, in the mu CMS or mu gamma gamma, mu BB value. Now the color coding tells you how well is the TT bar axis at 400 GeV fitted. Again, dark colors are very good. These are the points that we find, and we see, yes, the N2HDM has enough freedom to accommodate these 2 types of axes. It doesn't look as good in the NMSSM shown on the right-hand side here. These are the points that we find, and we can see that, yes, the gamma-gamma axis at the CMS can be accommodated, whereas the BB bar at the same time cannot. The structure of the Higgs sector is so rigid that it correlates these 2 quite strongly, and you can't get one large and the other one also large. Yeah, this is not possible. But still, if we say, yeah, maybe lab only 2 sigma, we throw this away, then also the MSSM is a very good candidate here. Now, the last point that I want to make, the third axis at the same mass, we have seen 2 axes, yeah, these are just the 2 plots that I've shown to you before. Very recently, CMS presented a new analysis, and they searched for Higgs bosons in the decay to 2 taus. And the question, when you see this plot, can you spot the axis? And people say, yes, of course, there is the one, but can you see it also at 95 to 100 GeV? And it's hard to see, but actually at 100 GeV it's 3 sigma, and at 95 it's 2.5 sigma, something like this. Better visible in this plot, that's also from CMS, where they show cross-section gluon fusion, decay to taus, and this is the cross-section for BB bar, Higgs to tau tau. If you don't see anything, the best fit should be here at 0, 0, but indeed they see this as the best fit point, and you can see here clearly the 3 sigma deviation that they see. And I think it's quite intriguing that we have effectively 3 axes in the light Higgs boson searches at the same mass. So, my slightly provocative slide. These are the 3 mu values. These are the sigmas that we find. Since we have 3 axes at the same mass, we can throw away the look elsewhere effect. We don't have to care about this anymore, and we can combine these. And I don't get quite to 5, but if you do this, you get at something like 4.3 sigma, which I think looks interesting. Now the question, can we fit all 3 axes together? And of course, we tried the N2HDM, and now we looked at type 2 and type 4. And unfortunately, because of the enhancement and the decreased structure of the couplings, in type 2 we find these points here. So, and this is the 1 sigma ellipse in gamma gamma and tau tau. We don't find points that can accommodate both. We can do gamma gamma, we can do tau tau, but not the 2 of them together. On the other hand, type 4 gives us these points, and we are very close, so type 4 does a very good job here. This is just the other overview here, gamma gamma versus tau tau, this works, and this is BB bar with tau tau, which also works. Yeah, just to show this, no problem at all. The color coding now tells us again how well the 125G Higgs is fitted, and again, no problem here. I want to say this is the analysis in the N2HDM. Tomorrow in the parallel sessions there will be a talk by Cheng Li from DESI, who looks at the same thing in the 2HDMS and gives more details about it. This is the overview where we show, again, these 3 axes. This is the gamma gamma axis. Yeah, this is here. And we can see that our points that we find are in perfect agreement with the mu value that they give out. This is the tau tau axis. We are not, maybe we don't go above, but we are slightly below, still very good. And the lab axis is also quite well fitted over here. Connection to the W boson mass. Can we also get the W boson mass out? In this model, if we want to explain the axis, we had to do another scan, because before, of course, we tried to get a small t parameter, the contribution to the W boson mass, but you can also get a larger one. Effectively, what you do is you change only the heavy Higgs boson part, yeah, which is more or less independent of the light Higgs boson part. And this is the plain W boson mass versus effective weak mixing angle. This here is the standard model. This here, these ellipses show you the 2 different measurements for the effective weak mixing angle, one coming from SLD, this one. This here is the one from lab, and this is the world, the so far world average. You can see the standard model is only in agreement if you take the average of these 2. This is long-standing 3 sigma discrepancy. Now, if we go to our model and we try to fit all the axes, but also fit the W boson mass, which is indicated by this vertical line here, we can do this. These are the points. Perfect. But it's then known, if you do it via the t parameter, you move down, well, you move up in the W boson mass, you move down in the effective weak mixing angle, and then only the SLD measurement would be in agreement. And then one has to think, well, what happened to lab here? But this is the situation. But this kind of problem you find in nearly all the explanations that have been put out after the W boson mass measurement came out. What can we do about it in the future? This is a plot that shows the limits that come, how to say, this is the light Higgs boson mass. This here is the coupling of the light Higgs to gauge bosons squared times the branching ratio to BB bar. This blue line corresponds to the lab exclusion limit. This dotted line is the lab expected limit. This is this 2 sigma axis. And then in our model, type 4, we are sitting here with our points. This line indicates what can be done at the Lhc 250. And the Lhc 250, of course, this is the lab expected, the lab limit. We can go down here, so we can probe substantially smaller couplings. And all these points that explain the axes are indeed in the reach. So the plus and minus collider at 250 GeV will be able to produce this new Higgs boson abundantly, and this will then give us the opportunity to measure its characteristics, its couplings, to a high precision. This is just, well, this is first a plot that shows the couplings of the 125 GeV Higgs bosons to tau plus, tau minus versus gauge bosons. Type 4 are the red points here. This was type 2, but forget about this for the moment. This is type 4. This is the standard model point, again with the high Lumi LHC ellipse and the ILC ellipse, and we would see a large deviation here. That is very nice. But, as I said, we can also attempt a coupling measurement of the new Higgs boson, because we can produce it there. This is shown via these red points here, coupling of the light Higgs boson to tau plus, tau minus versus gauge bosons. These are our points, and these little green circles, which are indeed ellipses, they indicate the precision that we can expect from any plus and minus collider, and you can see that the couplings can be determined to a very high precision, which will allow us really to pin down the underlying parameters of the model with a nice precision. I come to my conclusions. The Higgs boson that we've discovered cannot be the standard model Higgs boson, so we have to search for additional ones above and below 125 GeV. I focused on 2 models here, the N2HDM and the NMSSM. We looked at several axes. First, the one at 400 GeV from TT bar with the 3.5 sigma local, and then I discussed the 3 axes at the same mass in the diphoton decay from CMS, the BB bar axis from lab, and then the new one, tau plus, tau minus, also on CMS. And if you combine them naively, but not too bad because they're independent, you get to 4.3 sigma. And this is the list of how you can fit these axes. For example, TT bar, you can do it in both models, also in the N2HDM in the 2 types. If you look at the gamma gamma and P bar at 95, you can also do it in both models without any problem. Then TT bar 400 GeV, gamma gamma at 95 again in the 2 models, so SUSY does a good job. But by adding more and more axes, it becomes more complicated. So if you add here, then BB bar, you only can do it in the N2HDM in the 2 types. And if you ask for the 3 axes at 95, only the type 4 can do it. But this also shows us that by looking at these axes, who knows what will survive, this will allow us to discriminate the various models that can explain it. Yeah? So we will see what the future will bring us. And the last point, remember, not all of these anomalies have to survive. If one survives, we are in business and we are fine. Thanks.
Okay, so very good talk, thank you. So you probably mentioned, no, but what is Atlas doing about those axes? You mentioned CMS, LEP, so can you comment again?
So Atlas, let's start with the gamma gamma axis. As I said, Atlas has this limit based on the 18 inverse femtobarn. I was told they're working on the rest of the data set, but it doesn't seem to have high priority for them. What they should do, improve their background estimates to improve the sensitivity. And the other problem is that you need simulations for the background, and they just so far didn't put enough computational time into it. I don't know whether they're doing it. CMS, I know they're analyzing the rest of the data set, the 2 final years of run 2. So something like 3 times, well, yeah, they will get to 140 inverse femtobarn from now 36 inverse femtobarn. And I'm not sure, but I think there are good chances that they will present these data this year at some point. Yeah? But they are working on it for quite some time already. And, well, I think if they see the axis again in the rest of the data, we are really in business. If they say nothing there, you can forget about it. But we will see. Experimental data will tell us.
Here, yeah, so, Sven. So you said that the standard model, the Higgs you have seen cannot be the standard model, and therefore there should be some misalignment that not very large. And in the NMSSM, you were sitting on alignment, I think. So you impose perfect alignment. How that, in the other cases, I think you were trying to see how precision measurements from the 125 would fit. I didn't see that in the NMSSM, since you already asked for alignment. So what is the freedom there?
In the NMSSM?
Yeah.
Not sure how to answer this question. We went to the alignment, or let's say nearly alignment limit, and then we did a parameter scan around it. So we have some contributions from the additional particles there. And I think I showed one plot. This one here, yeah? So we see very slight deviations coming from additional particles or so, but I see, for example, here for the coupling to gauge bosons, we are nearly at the standard model value, a very small deviation only. And for BB bar, it's in a few % range, but yeah.
And so this light Higgs one...
This is the 125 GeV Higgs boson, yeah?
Yeah,
here
no,
we
but
didn't...
when you try to put the 100 GeV-ish Higgs, so...
Yes?
So how much mixture that has with...
Normally we find the singlet component of the light Higgs is at the 90%, 80-90% level, something like that.
Okay. Okay, thank
Yeah,
you.
so this you need. Yeah, you need some doublet component to couple it to the standard model, yeah?
Okay, very good. So indeed, some of these games were played at lab with CP violation with Marcella and Alice. So I have a simple question because most of these questions have been already asked. For the 400 GeV case, do you need why you need a singlet? I mean, what happens if you have a 2 Higgs doublet model, a simple 2 Higgs doublet model? What prevents you from doing that?
So the reason why we looked at the models with a singlet was that we never planned to look at 400 alone. We wanted to look at 400 plus 95. Pedagogically, I presented it in a different way. In the MSSM, I don't think you can do the 400 because we know that all the Higgses have to be very close in mass, and then the charge Higgs is also very low and contradicts.
I'm saying
general. With the singlet, you have more freedom, and you can get also to the alignment limit or closer to the alignment limit for lower, for somewhat larger masses there. Yeah, so in the NMSSM, this can be accommodated still.
Yeah, okay, I understand the MSSM gives restrictions in the quartic couplings, but in the 2 Higgs doublet model, you have more freedom than the MSSM. So, of course, if you start playing with all these Higgses, which you have to put them very light, okay, 95 or 100 in this MSSM, then you also have to worry about other constraints because the charge Higgs might be also light. You may have to worry also about other constraints like BS gamma, for example.
Yes. But,
I don't know whether this has been, that's my last question.
We took this into account. So they are okay.
What is the charge Higgs in your case?
The charged Higgs mass is a bit higher. I think we found it at 500 GeV or so, but in the paper there are plots about this. It goes from 500 and above.
What other decay modes does the 400 GeV Higgs have? Where else do you find it directly rather than indirectly?
Yes, we also looked at this, and the decay modes of this one, of course, well, it has to go to TT bar, yeah, as we've seen, which is the best possibility. Of course, it also goes to BB bar or so, but there are not many possibilities. So I think TT bar is the real mode that you have to look for, yeah, for the 400 GeV. In the NMSSM, we also looked at the case where the other Higgs bosons are then sitting, and there are possibilities to look for the heavier Higgs bosons as well. Yeah, but I skipped this here for the sake of time. But there are possibilities to discover them as well. Finally.
Last question. You have the last one.
Excellent. So then regarding the 400 GeV, could you show it again? So then that, Yeah,
This one.
that one. So does it bother you that the excess is just at the beginning of the spectrum where TT bars start to... So
Well, 400 GeV is the first data point, but if one looks at this peak dip structure that they were expecting and that they are seeing,
and
they seem, well, I don't think they would have put it out if they weren't sure that they can go to 400 GeV. Atlas, I think, is more hesitant. They started at somewhat higher masses.
yeah, that's precisely my question. So
yeah,
then,
this is
okay, very
well,
good.
I'm a theorist. I'm not here to judge our experimental friends and tell
No,
them,
I
look,
wonder
I
if
don't
that
trust your analysis.
worries
Yeah?
you a little bit. Okay.
Well, this is what they did, of course. This comes from the interference of these diagrams. Yeah, this is why you get the structure, and this is what they are seeing.
Yeah, it's very strange because you know the continuum interference is very bad there. So it's very strange. So I don't believe in this. Okay.
Then take 95.
95.
As he said, one is enough.
Yeah, exactly.
Okay, thanks.
Okay, so final talk in this section, and we now turn from LHC
το πάνω, δεν έχει...
G-2 to gravitation.
Δεν αντικατάσταση. Δεν ξέρω, θα δούμε στο τέλος. Thank you very much for the invitation. Is there a microphone that I can carry with me, or do I have to speak here? I speak here. Okay. Yes, thank you very much, the organizers, for the kind invitation, and also thanks to the previous speaker for agreeing to speak earlier. Hindsight advice: you know, even if you do have a car, don't drive here. Just take the bus. Right. So I'm going to be covering gravitational waves and the most recent results from the LIGO-Virgo Kagra collaboration. The pointer here. Oh yes, thank you. Yeah. Right. So we do have a. Thank you. Right. So when trying to put together the talk, I was starting to think, you know, what of our results, which subset of our results would be the most interesting for people in this crowd, for supersymmetry theorists and phenomenologists. And then, well, I took a dive into the literature and, you know, the different mechanisms that you guys have been working on, and I found quite a few things that maybe, you know, are interaction points. But very soon I lost hope and kind of got lost. So I decided to go the other way, obviously the lazy way. So I will kind of present what I think are the things that may be of interest to you, and you know, knowing a thing or two about physicists and in particular theorists and phenomenologists, I'm pretty sure that, you know, if something interesting shows up, you know, we just as soon as we put it out there, you know, people in this room will just jump on it and go nuts. So. So we'll spend some time describing what we have seen so far and the instruments that we are working with that are giving us these beautiful results. I will spend most of the time on describing the tests of GR, that the fundamentals, the testing fundamental physics with gravitational wave detections, mostly the nature of gravity, but also having to do with fundamental interactions and fundamental fields. And then very brief look to a couple of peculiar observations that may be of interest. I will not cover stochastic backgrounds because I noticed that there was already one talk that was related, and there is another talk, I believe, tomorrow afternoon on stochastic backgrounds. And maybe, if there is time, briefly to describe the prospects with future generation of detectors. So these are the beautiful instruments that we've been working with, the two LIGO detectors in the US and the Virgo detector in Cascina in Italy. And most recently, we had added to our network of detectors the Japanese Kagra detector, which just joined the network at the very late third observing run. So we have so far, and this is, of course, these are all the different institutes that contribute to the LIGO scientific collaboration, which I'm also part of. Right, so very brief history of what's happened since 2015. We've gone a long ways since then. So like in particle physics, where you have year 1, year 2, etc., we have our observing runs. So we started with 01, starting in September 2015, and if you remember the story very quickly, this is what we saw, a very whoopingly loud gravitational wave from a black hole binary. That was the first, and since then we are here. You can see the blue and the orange dots are the black holes and neutron stars, respectively, that we have observed in triplets. So you know, two compact objects in the progenitor and one final black hole. And this is quite a populated kind of plot. So the y-axis is the mass of each object, and you can see here the evolution in the rate of detection. So from 01 to 02, and 03 was last year. Well, actually 2019, 2020. Huge gap between the gap of memory as well, and you can see the very sudden change of rate of detections due to the upgrades between 02 and 03. And now we are coming close to the beginning of 04, where our detectors' sensitivity will be boosted again, and we have a broader reach, which kind of gives us access to a much larger volume of the universe. So we expect to have a further quite dramatic boost in the event rate of detections. And then Kagra will also contribute to this network with relatively low sensitivity in the beginning, but then we'll catch up. So this is the currently updated. So you can see it was very recently updated. There was a kind of delay by 3 months in the beginning of 04. And this is where we stand. So a couple of words on what we do in gravitational wave data analysis to test the physics and look for new physics. So obviously we have 2 stages in our analysis. So we have to deal with a direct problem, which is already quite hard. So given a gravitational wave source of known properties, what is the emitted gravitational wave signal? And then for this, you know, for decades, this problem has been attacked both from the analytical perspective and with numerics. And you can, I mean, it's a PDF, so you cannot see the video, but this is one of the numerical simulations at very high resolution, showing a binary black hole merger. But we also have to deal with the inverse problem, because our data is very noisy. So namely, given a stretch of noisy data, can you infer the properties of the source that emitted the signal? And for binaries, in particular for black hole binaries, this is the parameter space that we have to explore: masses, spins, sky location, orientation of the source, etc. And you know, using Monte Carlo or Bayesian inference methods, we end up with posterior distributions on the source parameters. And we use them, we extend the parameter space to account for possibly new physics and put bounds on those. So the typical thing. So when testing fundamental physics, like, you know, the nature of gravity and gravitational waves with our data, what we are testing is actually a combination of many different things. So we test the generation of gravitational waves, the propagation, and by detection here, I mean the projection of the signal onto the output of the detector. So mainly, for instance, you know, the gravitational wave polarizations will give you the final output on the detector data stream. Together with this, implicitly, we also test are away from systematics. So, you know, an analysis can be at most as good as our model. And also that model includes the model for our detector, noise, and calibration. So these are like implicit kind of information that we silently test, include in our tests. But we are trying to distinguish between the real physics, of course, and the things that we don't care so much about. And I think we're doing a thorough job at this. Related to our model, you know, for compact binaries, for coalescing compact binaries, this is a problem of the two-body problem in GR, which is we have to attack in a perturbative way. And this is a simple expression for the signal, so the strain, you know, including the plus and cross polarizations that we expect to see. And you can see an amplitude and a phase. The phase evolution is determined by the GR dynamics for binaries. And you can see that the coefficients of this post-Newtonian expansion, where the small parameter is the orbital velocity over the speed of light, these coefficients are determined by GR. And the functional dependence on the intrinsic parameters, so the masses and the spins of the two bodies, are determined by GR. So this is for the in-spiral, and of course this is not the end of the story. Numerical relativity have to complete the picture during the very nonlinear merger phase. And then black hole perturbation theory, together with numerical information from numerics, will give us the ring down, the final stage where the final black hole is ringing away its asymmetries and ending up in a quiescent Kerr state. So in our analysis, we have a number of models that are in-spiral merger ring down models that describe the entire duration. And I will briefly show the most, main results of our analysis relating to testing the nature of the compact objects that we observe, the nature of gravitational waves, propagation, and the generation process. One of the tests that you can perform that doesn't need to know anything about the underlying possible modifications in the underlying theory is whether your signal is consistent with itself. So the in-spiral part of the signal is consistent with the post-in-spiral part of the signal, namely that they predict the same final mass and final spin of the final black hole. And this is like a demonstration of the events in the before 03 and the events in 03. And you can see that, you know, GR lies at the 0 point on that plane, and the events are nicely, the posteriors are nicely distributed around this GR value, predicted value. These are deviations, possible deviations from the mass, the final mass and final spin that is predicted by the GR model. And we see a pretty consistent picture. There are a couple of posteriors that you can see that are off the center, and these are mainly attributed to weak quality in the post-in-spiral, I believe. But in any case, you know, when you have a few tens of events to analyze, these are 90% contours. So, you know, statistics will tell you that eventually you will get something that is off, and as long as it's not terribly off, and that you know, and the base factor is consistent with, you know, the distribution that you expect, you don't have to worry about. So, I mean, in the next few slides, I will show results that are quite disappointing from people who are looking for new physics. But in any case, this is what we have. The other type of test that is one of my personal favorites is probing the post-Newtonian in-spiral dynamics. So the binary dynamics, and allowing for a modification in any of these post-Newtonian phase coefficients in the expansion of the phase to vary. And these are kind of very typical effects that are predicted by pretty much any modified theory that you can come up with. So modified gravity will, or even a modification in the nature of the compact objects or the environment in which they merge. So also interesting from a particle physics perspective, would modify the dynamics, the binary dynamics, and this would be manifested as a modification in the post-Newtonian expansion, in the coefficients of the post-Newtonian expansion at different orders. So here you have, I mean, Newtonian order is here, and you have 0.5, like a half PN term here, 1 PM being at phi 2, etc. And you can see that we have put bounds on possible deviations from the GR predicted values. So these are all upper bounds. And of course, the lower you get in, the higher you get in post-Newtonian order, the further you probe the late stages of the in-spiral. So the last few cycles will give you most information about the high order post-Newtonian terms, the low frequency, in the early in-spiral will give you information about the low post-Newtonian terms. So it's no wonder that the single Newton star binary event that we're using in our analysis is dominating the -1 post-Newtonian test. And these are the combined posteriors that we have on these post-Newtonian coefficients. Further on the nature of the black holes, or the compact objects that we believe are black holes in the binary, it is well known that once you know the spin and the mass and the spin of a black hole, you know everything about it, all the properties. In particular, the quadrupoles, the multipolar expansion of space-time. So the spin-induced mass quadrupole for Kerr black holes has a coefficient of 1, but this is not the case for exotic compact objects, either with some matter content or in modified gravity or other like vacuum configurations, more exotic configurations. This is a contribution that comes at the second post-Newtonian order in the expansion, and you can probe and you can see that these are also well constrained to be, well, the posteriors, the bulk of the posterior is consistent with with 0, which is the GR predicted value for the deviation.
What are the typical deviations in this modified?
So it depends what kind of object you are looking at. So you know, if you have a neutron star or a boson star, this can be quite large, tens, yeah, in the tens, I guess. So once you know, if you stack information together and you ask, you know, whether all these objects are black holes or boson stars, then you can come up with a constraint like this. For other cases like gravastars or more exotic vacuum things, I think the deviation is smaller, but yeah, this is very model dependent, of course. Yeah, for boson stars it can be in the hundreds, I think, not only, yeah, much larger than neutron stars even. Probing the ring down, so like I said, the final state is assumed to be a Kerr black hole, and we, you know, the way it is settling down to a Kerr configuration is by wringing away the non-axis symmetries of the final, like peanut-shaped unified horizon, and in the form of gravitational waves that are of specific frequency and dynamic time. So these are the known quasi-normal modes of the final black hole. I mean, this is it takes a bit of time until it gets to the well, that this quasi-normal mode spectrum approximation is a good approximation because, you know, you have a stage between the time of the merger and about 16M after that, where you have highly nonlinear effects. So you need to start your analysis far enough from the merger time that you can expect your model of a superposition of damped sinusoids to be consistent, to be accurate. So one thing I wanted to point out here is that so far we haven't been able to probe much more than the dominant mode, the L equals to M equals 2 mode, the fundamental one, so no overtones. There are weak signs of the presence of overtones and perhaps a secondary mode in one or two binaries, one or two events, but nothing conclusive. So not with much confidence. So the prospect for the evolution of this kind of test is quite interesting because, you know, in the next, hopefully in the next few years, we will be able to probe multiple modes for each event, for the loudest events, which means that we will be able to perform a consistency test between the frequencies and damping times of each of the modes observed. Since, you know, once you observe a mode, you can pin down the final mass and final spin of the black hole, and then everything else that you observe after that is pretty much a consistency test with the theory and with the actual nature of the compact object. But further, you know, post ring down, is there anything else, or could there be anything else beyond there? And theory tells us that it's possible to have an exotic compact object that instead of a horizon has some structure where modes are trapped in a double well, for instance, in the case of a wormhole, for example, or a gravastar or some other exotic object. And so modes are leaking away in the form of echoes that, you know, as they bounce up and down in this potential well, and they leak out towards infinity, towards the observer. And we have been testing for these echoes, post-ring down echoes, with both modeled analysis and an unmodeled analysis that is looking for any kind of echoey type of signal after the ring down. And this is kind of the best summary plot that I could find, which is mainly, thank you, giving a distribution of p-values. So having been looking at plots of particle physics, you're probably very familiar with p-values, and this is pretty much consistent with no presence of echoes in the events so far. Another very interesting and very generic effect that you may have in either modified gravity or well, essentially a theory that predicts a modified dispersion relation in the gravitational sector is, well, dispersion where you have gravitational waves at different frequencies traveling at different speeds, lower than the speed of light, slower than the speed of light. And this will induce, in the case of a massive graviton, this is what the effect would look like in the phase, so an additional term at 1 Poissonian order. A generalization of this is a case where you have modified the dispersion relation for the graviton, whatever that is, with an additional term that has a certain a monomial in the momentum. So in the case of the massive graviton, this would be alpha equals 0. But then you have Lorentz invariance violating theories where you can have any kind of exponent in here, or even more complicated things like contractions of this with some tensor. So most of these, except for a special case of alpha equals 2, will break Lorentz invariance in one way or another. And then you can probe the length scale of this effect. And basically you can put constraints on the amplitude, because so far we have not observed dispersion in our data. There are particular theories that predict such an effect, but I'm not going to focus on those. I'm just going to give mainly the current bound on the mass of the graviton, based on the fact that we don't observe dispersion in our data. which is currently at 1.27 times 10 to the minus 23 electron volts, which is quite a small number, I believe. And this is a plot describing the constraints from the latest data set in comparison with the previous data set in the gray triangles here for different values of alpha of this exponent, both in the subluminal and superluminal sector. And finally, we can probe after the propagation effect, we can probe also the polarization content of gravitational waves that we have observed so far. So the gravitational wave signal is projected on our detectors with what we call the detector tensor, and this has a different kind of projection expression for the different polarizations. In GR, we have two polarizations, the plus and the cross, for gravitational waves. In modified theories, this is again an animation that will not show in the PDF. In modified theories, we can have 4 more polarizations. We can have longitudinal modes and the breathing mode. So far, we have seen no evidence that any of the alternative hypotheses, alternative models that include the possible presence or either a scalar mode or a vector mode. So these are all, well, so let me explain what we see here in the different columns. We have the competing hypotheses and the base factor of those against the simple tensor model for GR. So by S, we mean a pure scalar, and by T, we mean a pure tensor model, and V is a purely vector model. And here we have also mixtures between tensor and scalar and tensor and vector. For this, the base factor is consistent with 0. For the pure models, we have more compelling evidence against. Yes. Oh, right. So I'm going to very briefly run through some special results from special events, like the first binary neutron star detection that gave us also an electromagnetic counterpart and allowed us to constrain the difference between the speed of gravity and the speed of light to about 10 to the minus 15, one part in 10 to the 15, and also the difference in the effect of the Shapiro time delay between the two signals. So these are very kind of generic constraints that apply to any theory that predicts a modification in the propagation speed for gravity. Also constraints on extra dimensions, since gravitational waves may leak into these extra dimensions. You can actually let me skip this. But if I may, one result that I would like to, and it's pretty recent, I would like to point out, has to do with additional fundamental fields, in particular for a very light boson. Whenever you have a very light boson whose Compton wavelength is pretty much comparable with the Schwarzschild radius of the black hole, you will get stimulated growth by the spin of the black hole. So you will have what we call superradiance, and we'll have a growth of a bosonic cloud around the black hole, which will eventually decay slowly and will give two distinct signatures. One is the direct gravitational wave signal during the decay with a continuous wave emission, and the other one is an effect on the population statistics. So the population of black holes in the mass and spin, on the mass and spin plane. So we will have, during the growth phase of this bosonic cloud, you will have a spin down, a rapid spin down with a short time scale for the black hole. Eventually you will have part of the parameter space of black holes being cut off from observations. So you will not observe highly spinning black holes for a given, a given mass. And this is something that people are very interested in looking into now that we have a decent amount of black hole observations and statistics. On the direct detection of gravitational waves side, You can set bounds by non-detection of a continuous gravitational wave observation. So the non-detection of a continuous signal has allowed us to put bounds on the presence of an ultralight boson, and this is one of the plots in this paper which I invite you to have a look at. This also includes a picture where you have an axionic boson, an axion-like boson with masses of the order of 10 to the minus 13, 10 to the minus 12 eV. And you can have different constraints assuming the presence of such objects at different distances. And we'll skip these special events, which are kind of question marks and not fully understood with the current astrophysics. And I will just leave you with a summary of the different type of effects that we may have with new physics in gravitational waves. Thank you very much.
Okay. Thank you, very nice talk. Two minor points. For the ultralight scalars, anything lighter than the 10 to the minus 13 electron volts, you have no constraints?
Yes, so the main constraint is that the Compton wavelength, so it's the mass of the particle will give you a Compton wavelength that has to be comparable with the size of the black hole, the length scale of the black hole, because otherwise you will not have the formation of a cloud in the required time scales.
Okay, thank you. And you didn't mention primordial black holes.
Sorry?
You didn't mention primordial black holes?
I didn't mention. I saw there was a talk about primordial black holes, so I thought that would be covered by someone else. Okay. So yes, I should have mentioned it in my list of things that I didn't mention.
Thank you.
What was the next slide?
So this is one of the very interesting events that we saw in 2003. This is the heavier, the most massive binary that we have seen so far, and most interestingly, the primary mass falls right into the mass gap predicted by astrophysics. So you have the mass gap due to the pair instability that, the lower bound of this gap has quite an uncertainty because it's model dependent, but it should range between about 60 and 80, I believe. 60 and 70 solar masses, I believe. So this black hole shouldn't be there.
Why wouldn't those black holes be circles of masses?
That is one explanation. That is a second generation of black hole. There are other things that are interesting about this signal. So I wouldn't put too much attention to, you can see that it's a very high, because of the very high mass, the data is mainly coming from the very final cycle, if it is a black hole binary, under this assumption, and the ring down. And it basically looks like a blip. It's very easy. It's, the underlying model would be quite uninformative, just because, part of a lot of you don't have any spiral signal to pin down the progenitor mainly. So, people have tried different things and have been able to match other models better than the quasi-circular black hole binary model. For instance, they have looked into dynamical capturing of highly eccentric black hole binary. Other people have looked into head-on collisions of procastars, and they managed to get a higher base factor. Of course, then you have to consider your prior, so the base rate for the possibility of having two procastars colliding head-on. What is that? What would be the event rate of such cases? And so but this is very interesting because it allows for interpretations further than a typical black hole binary that you have in your cohort.
No more questions, so let's have the speaker.
Okay, well, so welcome back. So we'll continue now with the next part of the program, and it's great to have Dimitri Nanopoulos to be the next speaker. Dimitri, please.
Good morning. Thank you for the invitation here. Now, what I'm going to discuss here is some efforts that we have made with different groups, and you see the names in a short while, about unification and getting things from the string directly. Now, that's the title of my talk. Is Cosmology and Phenomenology from the superstring no scale flipped as U5. Now, here, yeah, good. This actually, I could spend with this thing the whole talk, but I'm not going to do this. What you could see here, this is from a paper with John Ellis, Keith Olive, Marcos Garcia, and Natsumi Nagata, that somehow we got some inspiration from the superstring, and we're using no-scale supergravity and flipped as U5, and putting these two together, we can get now some coupling through here to go to the sort of... I think you need to speak to the microphone. I need the microphone. It helps. Now, so we have, the one helps the other, and for instance, as we're going to see in a moment, we can get easily Starobinsky-like inflation from here with all the fallings of we know, and then we can move on and we get some strong reheating, and we get all the properties that we need to have, gravitino production and dark matter, and from here leptogenesis, and so on. Now, all of these things that you see here, we have done it in an effective theory, right, from this thing. We have made the correlations and everything and stuff like that. The idea here, it is, if it is possible to somehow to get this thing inspired, because we keep doing inspired, as you know also, and you have talks here, we have to be very careful if we start with a bottom-up approach, with vis-a-vis if there are problems of ultraviolet kind of completion and stuff like that and so on. So we'll try to make some efforts here with Ignatios Antoniadis and Yannis Rizos, who is actually from this university here, and getting this stuff from the superstring-derived SUSY flipped as U5. Now, let me say right away that in this case, we can calculate, we have full calculability, both from the no-scale part, for an effective part that we're going to get, and also for the gauge part. So both of these things can be, we have full calculability, and then you see here some papers, some old papers anyway, that we put in use, that you can see how we can calculate this. I'm not going to go through the calculation, obviously. I'm just going to use the results that we have done. Now, let me just remind you in half a second that in the case that we have the flipped as U5, the different fields, maybe you have heard about this, is the 5, the 10, and then what is happening is because we have this, the flip between the up quark and the down quark, the right-handed quarks here, you have to put the charged leptons outside, and then because of this, then we have to have here a right-handed neutrino, which is good, of course, because of the story of we know that the right-handed neutrinos are there because we have mass for the neutrinos. The corresponding Higgs now, as we maybe have heard, that I don't need to use adjoints, and that's a good thing from the string. I think it's the only model that I know that we don't need to use adjoints, and we can do it with a 10 and a 10 bar, and then you can calculate the potential here, the different terms. I would like the different masses here, down, up, charged leptons. Here we have this the doublet triplet splitting here, and this is a very fundamental one. Please remember that one here, which is a 10 and NH bar, the Higgs here, and a singlet that we need to have in this model automatically. And then we use this kind of Lhc Kunas, etc. Potential, who has been derived after by Ed Witten from the string, and then we're using this thing as an effective theory to do our business here. Now, one point here that John did in the morning, it is that here, of course, we have an extra gaugino here because of this U1 here, which does not need to satisfy the universality conditions if you want to use universality, and also because we have this right-handed singlets out, and for instance, in the case of G-2 is mu, and that's why if you remember in the morning that you can use different values from this thing here and from this thing here, and then we can even maybe explain a part of the G-2. Now, let me now present this story, how we can get this kind of thing. The gauge group, I'm using the fermionic formulation that has been developed by Ioannina, Bahas, and Kunas for this thing here, using on the theoretic string. And then the group that we're getting, it is, of course, you have to have the boundary conditions, and because of the boundary conditions, then you can get now, you can choose the boundary conditions, and then actually the model that we're using here is a model that we did back in '89, and this is what we call the revamped model with John Ignatios Antoniadis and John Hagelin. And this is actually, this is the gauge group here, the observed part SU5 cross U1, and then we have this extra U1s here, and then you have now the hidden group in SO10 times SO6. Well, we have now actually, in this case, SO6 is good because it says U4, and then we're going to have some fourplets that they're going to have some funny charges, but then we're going to have confinement for this thing, exactly like what's happening in QCD. Now, here it is the superpotential you can write down at the tree level. I'm going just to present some terms that we want here. That's one term here, that's another term here, it's another term here. Now, these three terms that you see here, this is basically that will correspond, this directly Yukawa coupling at the tree level, and this is going to be the bottom quark, this is going to be the top quark, and this is going to be the tau lepton mass, right, for this thing. And for instance, you see from the very beginning that the coefficient here is the same for the bottom and the top, and so this kind of things that we're getting back in the 70s, it's back here. And then there is another term which is very fundamentally what I'm going to say in a few minutes. It is a term that it is an F4. This is a decaplate, and F5 bar. This is going to correspond to the H bar, and this is the singlet here. So that's a very fundamental term that's going to play a very important role to our discussion here. Now, let me just remind you in a second that it is together with John and with Keith, almost 10 years ago, a month after almost the Planck 13 data came out, then we knew about the R-square, et cetera, and we tried to find out something that can come out from supersymmetry, supergravity of the string and stuff like that. And then we noticed very easily, that if we take the no-scale supergravity model I presented before, and we plug in the simplest possible superpotential here, actually it's a Vesumino superpotential, we can put it here, then in this case, you're automatically getting a Starobinsky type model, of course with corrections, because this is a real theory. And one thing that I'm trying to do here is I'd like to stress the following thing, that you see here, this is the corresponding Starobinsky term, and then you have these extra terms that we have, and you notice always here that we have a positive term for the Higgs boson, for the term that breaks SU5 cross U1, and then you can see from here, and you can check it, that we don't have during inflation and during even after when we have reheating, SU5 cross U1 is not broken, is in the symmetric phase. This is a very interesting result because we're going to use in a moment to make some physics out of it. So this is what we're discussing about this kind of thing. So we discussed with Ignatios and Yannis about this superpotential, and Ignatios was adamant that we cannot do a string model with such a kind of superpotential, and also because also we like to explain, of course, that this mass here, is 10 to minus 13, and these coefficients have to be very exactly what it is, and so on and so on. So basically, we have now another hierarchy problem, if you notice, right, for this thing. We have about this intermediate mass for the inflation scale, right, for this thing. So what we did, it is, we have written something with John and Keith when we make a classification of what kind of superpotential we can have, and we got one there that will look very interesting, and we can go after it to get it from the string. And lo and behold, what is going on here, it is, first thing is, let me tell you, this is the Keller potential that we get from the string. So this is, we calculated this. So this is not, you see, it does not look exactly what we had used before, right, for this thing. We just calculated this. So you can calculate it explicitly, this kind of thing here. And then we have these two fields, the Z and Y field here. And then also we calculated this, as we're going to see in a moment, the superpotential that we have these corresponding couplings here. And actually, let me tell you right now, if you go and plug in and do your, this is a first year graduate calculation, then you get here, of course, Starobinsky gain in a different, the same kind of model with the different corrections that can be different from what we had it before. Now, the thing is, what it is these two fields? Actually, what we're having here, you remember that we have this term that couples the singlets with the heavy Higgs and with the decaplet, and this is very important term because this is the singlets that they give masses to neutrinos that you observe at low energies, because we have a double seesaw mechanism, right, for this thing. We have the first part down here, and then we have the second one here, the standard story that we use these days, and these terms, exactly, it is one of these terms that's going to be the inflaton in our case. And actually, we found at the tree level, there is a term like that, and then you can, basically, you can have from here a massive part, and then we have now a massless part here, which is going to be the inflaton, right, from this kind of thing here, and then you go and calculate to see what we can get from this thing. And then after a lot of calculations, Yannis is not here to tell you how much it takes, but we are confined anyway because of COVID, so, we tried and stuff like that. Then what is going on here, so we get now the potential, the superpotential that we get, who looks very much like this one here, and then we have now all of these things are corresponding constants that you can calculate in the string theory and this coefficient and stuff like that. And where is Miriam here? Here it is. And actually, some of these things say, well, it's orders of magnitude and stuff like that and so on. But she wrote with her students and her postdocs a paper how to go and calculate this in front, not the non-normalized terms, but even these coefficients there from this thing here. And then you have to be very careful with this thing here. So this is the two terms that we have here. And then Yannis Papadimitriou. Okay, fine. Sorry, I forgot. Always I'm for a Greek name. Anyway, so here we have now, you notice now this term here, and then you see what we have here. We have phi 3 bar and phi 3 bar square. So you see this thing here, and you see with the constant here, it's exactly the terms that we were wanting to have in order to get this kind of superpotential, in order to get the Starobinsky thing. I repeat, there was a lot, thousands and thousands of terms from this thing. And we found a single term at this 6th order, and then we get another single term in the 8th order, right, from this kind of thing here. Now, and then you see now to do some, to put some numbers in, then we parameterize this thing the following way, and then basically what we do is in this type of models, it is generic that we have now what we call an anomalous, these 4 U1s, if you go and see for them, one of them, it is anomalous. Of course, it's not anomalous, we're doing string theory, right, for this thing, and then we use the Dine-Seinberg-Witten mechanism, right, from this thing here, that you shift the dilaton and you get this Xi factor that goes all over the place, and then this place here, this psi square, it's about this number. I mean, it is this number, and then psi is about 1/10 of the string model, which means that I can use this number to do perturbation theory. And also, because of all the singlets that they have anomalous or not anomalous U1s, right, for these things, they are all related. So when you go to do the flatness condition, then you get relations between them. And actually, that's what we spent all the time for this paper. And if you go, it's about 50 pages paper. If you go and look at it, most of the time, it is the flatness conditions that we're talking about and how to satisfy them and stuff like that. And so that's what the parameter that we're using here, which is calculated dynamically, right, from this thing here. Now, and then you go and you put, here it's the analogy I'm using about, right, from this kind of thing. That was the term I wanted. Here the corresponding terms here. And then if you go and use, and we were using generically psi, because of course, one thing could be 1/3 of psi, or that'd be 1/√2 of psi, or whatever it is from this thing. We're using generically this psi value for the vacuum excitation values that were coming out from the flatness conditions. And then what we do here is we go and calculate now this scale, and then you see what's happening if you plug in the numbers for what we're using, and I repeat, we spend some time to do it correctly. Then you see now you're getting this number here, which is just 10 to the 13 GeV. So it is a higher order term coming from n = 6 and n = 8, this kind of thing combination here, and now we go dynamically for this thing. Of course, because the inflatino, if you want, whatever it is, it's related, is involved in the neutrino masses and stuff like that. So we should not be surprised now that we find a connection, because always was very strange why inflation occurs at 10 to the 13 GeV and stuff, right, for this thing, which is very near to the case that we expect the right-handed neutrinos of the order of 10 to the 12 GeV that we know for years, right, in order to do business for this thing. Now we know. Now the answer is very simple. Now, because it is the same particle that somehow the same supermultiple that involves in one case and involves in the other case, and of course supersymmetry breaking is very small, so that's why the inflatino and the inflaton, if you want, have the same mass. So we get this explanation here, and now, and I repeat again, that this is a calculus. We calculated this number, we calculated this superpotential, we calculated this number, and turned out to be on the right kind of thing here. And here I have some comments. I don't have the time to go through this kind of thing here, that we have what we get some different kind of, because you started with psi, but then of course it's not every field that is going to get a psi thing, because then you have to satisfy the flatness conditions, and then in order to satisfy the flatness conditions, you get a lot of equations, and then you get types of this form here and so on, just to show how business is happening. Now, let me now go to the neutrino thing here that I was talking about for this thing, because now you see what's happening here. It is the super pattern of the inflaton here. It is decaying. You see it's coupled for here. It's mixing with the right-handed neutrinos here, and then what you get, it is you can get now, because that's going to give us the reheating, right, for this thing. But you have to be very careful how you do reheating, right, for this thing, because you can hurt yourself with if you have a lot of big number here, because then you're getting too many gravitinos, and that means you're getting too many neutralinos and stuff like that, and then you don't know what to do. And inflation has finished, right, from this thing here. Though here, there is another thing that's very important in this case that we're discussing. It is, I told you that SU5 cross U1 is unbroken after I finish everything with inflation. And now what it is happening, it remains unbroken until what is going on here. We have now an SU5 cross 1 vacuum and SU5 and this broken vacuum, right, for this thing. But while this was broken, then what you have is we have now a lot of degrees, light degrees of freedom, and because of the minus pi square over 90 t to the fourth term here, now what's happening is this is actually where the universe is staying in this phase, in SU5 cross U1 phase. And it takes some time before we reach a point that we have now the difference to come up, and then what's happening is as U5 cross U1, it becomes confined. This is exactly a scenario that I have with Keith and Kyriakos Tamvakis back in 1980 or 81 or something like that early from this thing here. And then we have now this flop, and then we have now that we're moving to the case of the real vacuum. Because of this and because of that, this is late, this phase transition, we have entropy generation. And because we have entropy generation, that we have to be careful to take into account in all these kind of numbers. And actually it helps us, and you go and calculate this. Okay, this is the neutrino story here. And now you see now, basically we're getting entropy generation of about a factor about 10 to the fourth or something like that. And then what is going on, it is of course now what's happening is because we have a late phase transition, the right-handed neutrinos, they're massless because the SU5 cross Yan was unbroken, right, for this thing. Suddenly it is broken around 10 to the 10 GeV or something like that. It's unbelievable that the numbers turn out to be on the same kind of thing. When you calculate the degrees of freedom from SU5 cross U1 with respect to the other, and you put the confinement, to find the confinement scale, you get always around this scale of 10 to the 10 to the 9 GeV, right, from this thing here. And what's going on now, then right-handed neutrinos suddenly they get masses, they find themselves out of equilibrium, violently out of equilibrium, and they decay. And that's what they create baryogenesis to the leptogenesis, Phaleron, etc., etc. I'm not going to go through this thing here, but then you go and calculate, and then you find out, and this is our numbers we're using, this is 10 to minus 11. Of course, all of these things that you say, it's happening after the superpotential, which is from the string, right, from this thing. Now then it is normal calculations, right, from this thing here. And now we're getting this, for instance, we can go and make some kind of scanning with these parameters, right, from this thing to see what we're getting. And then what we found, it is we're getting some very interesting results and some interesting correlations in this case. And for instance, here we have now about the baryon asymmetry, right, from this thing, that also we can calculate the sign of the asymmetry. It's very interesting that we can go, you have to follow through the whole, and you can kind of sign to get the right sign. And then here you see the case of one and another, and also you see here that this entropy generation that we got of 10 to the fourth that we can calculate with normal numbers, right, from this thing here, plays a very important role into making the density, the dark matter density to be on the right side, and also the baryon asymmetry to be on the right side. And then you see here, for instance, that you get now out of, I don't know, 2 million points and stuff like that, and you make this kind of normal ordering or inverse ordering, right, from this thing here, and you get now, this is what we observe experimentally, the standard number, and then you see now that we're getting to a point when we get enough points to justify that it is not a fine-tuning or something like that. And then you can get the corresponding relation between dark matter and the baryon asymmetry, and also you see we're in the center of things here, and then the same thing between delta, this entropy factor, and MLSP, right, from this thing here. And actually here we make a very specific prediction. The prediction that we make here, it is for the whole framework here to work. Then what is going on is we have to have supersymmetry to be above 10 TeV. Now, take it as you want, right, from this kind of things, and you see from these things here, everything in order to fit, we have to have rather heavy supersymmetry. Now, so we make some fixings. Let me go on, and I would like to come now and finish with this kind of thing here, because I left now something for the end. Now here what you see, this is from Ioannina, Ellis, Hagelin, etc. in 89. And this is from this paper, that basically we have the corresponding term for the top quark, and then if you go and plot, right, for this thing, this is the top quark coupling at the GATT scale, and it is at MW scale, and actually we have an infrared point here. And now what you can see here It is basically whatever you do, you have a limit on this kind of, because you have infinite point here, and then you see, if you go and check these numbers and put the real numbers in, we're getting now there, first it is less than 190, right, for this GeV, and then we get something which is between 170 to 180 GeV. It has been predicted at that time. Now, what's happening is, then you say, and then this was in 89, and then when it happens in 1995 for this thing here, then you say, why you didn't mention this? The answer is simple. We forgot, right, from this kind of thing, but it was there. Now, so that's one thing with this mass here, and also the same story with the B and the tau. Now, here, and I'm finishing for this thing, is now you can go and calculate, now I'm in the phenomenology part, and you go and calculate the fermion masses, not the supersymmetric masses. There's some experimentalists that were telling us, always they're telling us about masses that we don't know. Can you calculate the mass that we know, right, for this thing? Now you see how we calculate the fermion masses, right, the ones that you know from high school, right, from this thing. Okay. Now, so what's going on here? Because they are not at the tree level, so what you do is you know the rules. We go and calculate higher orders, right, for this thing, systematically, one after the other, right, from this kind of thing here. And here we have now a term like that for an up quark, right, for this thing, with one vacuum excitation value here, and that would correspond to the charm particle. Then we have now quarks, down quarks, that will correspond to the S particle here for this thing, and that will correspond to the muon, right, from this thing. Now, and then, of course, that's how we identify the generations, right, from this thing. Now, what is going on here? Now, for instance, I will come to this point in a moment, because we know what is the vacuum excitation values, and you can calculate, and then you can see, for instance, something that it looks a bit funny, that you have now this coupling here, and the coupling with the muon, so somehow it looks like the ms equal to mu. Now, for the older of us in this office, it is getting there. It is an old story about I know now that ms equal mu is a wrong relation, right, for this thing. Ms equal mu over 3 up there, right, for this thing, and becomes ms equal mu right down here, right, from this thing here. Now, and then I will come for this explanation in a moment. Give me 1 second. And now here it is about the up quark here. You can calculate, you plug in the numbers that we use universally, and then we get now this relation that it is psi-phi m top, right, for this thing, which is a good relation. And then we go through and we do all this analysis here from this thing. And let me just give me 1 moment. And here it is how we can get now this relation mu equal 3. You can get now mix this F2 with F1, which is getting the big vacuum excitation value, and then from here you get this term here that you can fix with the relation with ms, and we can get this kind of relation that we want. And now actually we're getting something which is very interesting. We're getting now the Cabibbo. I have just put the numbers there, all the numbers for, to see, and then we get now this mixing with the Cabibbo angle here, and this is psi to 1/2. It's basically 1/10 to 1/2, which is basically on the nose with the Cabibbo angle, right, from this thing here. Now, so here it is our proposal here for the masses, m top, mb, m tau, mc, etc. And that's, I don't know, to my knowledge, and also we get the electron mass, which is right on the nose here through this non-normalizable couplings. And actually, for all this together, I have never seen it before. I don't know, maybe I'm missing something, maybe I'm getting too old, right, from this kind of thing here. But now, you see now with 1 parameter psi to getting now all these relations here, it is the first time we were seeing, right, from this thing. Now, let me now I'm going to, yeah, you have seen this again. No. Let me finish with this kind of thing here. Back in, whatever it is, in 1990 with Jorge Lopez and John, we wrote a paper on these issues here, and we have found some confinements and stuff like that, and we were very excited. And at that time, we wrote this kind of thing here. We say, we leave it to the reader to decide how many more miracles she wants to see before abandoning her doubts about flipped SU5. Thank you.
Thank you very much, Dimitri, for the interesting talk.
Thank you.
And questions, urgent questions? Yes?
Very nice work, and thank you for the nice talk. I have two quick questions.
Yes.
The first is about the neutrino, ordinary neutrino masses.
Yes.
What hierarchy do you get?
We get, yeah. Look, this is a talk not for a half an hour, right? For this thing is everything here. But, okay, so this is not my time.
Sorry. Sorry. If you want, we can discuss it in private.
Yeah. Anyway, yes, we get, and also through the scanning that we did and stuff like that, we get normal ordering.
Normal
ordering. We got something like 9,800 cases of solutions with normal ordering, and we get something 700, Keith knows, 740 or something like that of inverse ordering. Right, for this.
Thank you.
And for us, it's very important, because if you go this to the proton decay, then you can see that if it was inverse ordering, then you get that the muon is going to be.
Yeah, that was my second actually question. Very good. And a very quick thing on the baryogenesis.
Yes.
You get baryogenesis through leptogenesis, through right-handed neutrinos.
Yes,
okay, the standard. Thank you.
I'm getting old. Anyway, the standard story, yes. Yes. So who's breaking supersymmetry? Oh, supersymmetry. Who's breaking supersymmetry? Yes. Now we're working on this kind of thing, but we have now with John and Keith and Sarunas Werner, we have this type of theory that was the effective theory, and we have found that we can add a term there, that this term, extra term to the superpotential, that it is first does not change the inflation story. Secondly, may provide dark energy at the level that you can justify it, that is at the level we find. And thirdly, breaks automatically supersymmetry in a kind of way. Now, we try now to combine this kind of thing, but that was effective theory, right, for this thing. And then we tried now to take this kind of thing here and get it, where is it, Matthew? Here it is, right, for this thing here. Check to see if we can get this superpotential from this thing. Okay. But of course, that's not all, don't tell me wrong, that's not the only way. We can use other ways also. Yes.
Okay. Thank you very much, Dimitri. Please think again. Okay, so the next speaker is Apostolos Pilatsis. And the title will be, I guess, there.
Okay, thank you for the invitation. My voice a little bit short, but it's not COVID, despite continuous testing and persistent testing. This is not. So my talk might be short because of my voice, whatever. Right. So voice problems. Right. So I will talk today, and also I'm very happy to be here. It's a very nice place, and I like to see this bridge. Actually, it's quite good to see this bridge. Right. So. The talk what I'm going to say today, present today, is a kind of review, and I would like to go also beyond this standard framework that Dimitri talked before, and I would like to talk about leptogenesis ideas which developed in the recent years, and they allow for a testable or observable such lepton flare violation for the experiments. Okay, so. this presentation here includes a recent work I did with one PhD student, Pablo Cadia da Silva from Chile, one research fellow, which came from Ioannina actually, and another PhD student from UK, Thomas Mackwell. So let me give an outline of my talk. So the first thing I will remind you, I think Marcella did a good job here, very briefly about the matter-antimatter asymmetry and the connection of that to leptogenesis. Then I will discuss something that was involved in the last more than 20 years, which is about resonant and most recently tri-resonant leptogenesis. Then I will not have much time to discuss all the technical details, but I will flash the complexity of producing a consistent set of transport equations to calculate that kind of framework, so which has to be flavor covariant, not just flavored. And then I will discuss what kind of charge lepton flavor or number violation you might see at collidas and other experiments. And finally, I will give some numerical estimates of some benchmark models and summarize my conclusions. So, so far we know that the matter, unlike the cosmological constant, which some people have claimed that might be zero, so we know definitely that the baryon asymmetry in the universe is non-zero, and actually two measurements which were compiled by Keith Olive and collaborators, we know that the baryon asymmetry from CMB and the baryon big magnetic synthesis plus deuterium give two very constraining and are independent measurements, and they are very close to each other. There is no discrepancy. And to explain that, we all know that you need, in a CPT invariant theory, you need the so-called Sakharov's conditions for generating the baryon symmetry in the universe, assuming implicitly, initially, a B-symmetric universe. And I will show how this hidden condition is not needed in the framework I'm going to discuss. So you need B-violating interactions, C and CP violation to deal with chirality of fermions, again in this CPT invariant framework, and of course you need to some form of Tauf of equilibrium dynamics. I should say in the FRW universe, the last condition is already fulfilled in some form because you have an arrow of cosmic time, okay? And the question is how much of that you need to obtain, to explain, to account for these results. So the popular scenarios of baryogenesis, just reviewing a little bit of this stuff here, is baryogenesis through the decay of heavy particle. So you may have a B-violating decay. This was back in 1978, and this was a good idea. You had to deal with problems like proton decay and also with problems with what I'm going to discuss with phalerons, making sure that the B violation is not also automatically has a component that violates B minus L as well, so that the phaleron interactions do not wash out. So this was a problem model building. Apparently, it was solved in 2012. I should say also from the beginning at this point that this field has developed from my last work, what I did in 2012 to 2014. So you can see here that another scenario of baryogenesis is at the electroweak phase transition. So, this proposal in 1985, you could have this perfect scenario through the nucleation of bubbles and through a first order phase transition, did not work in the standard model. And apparently, yesterday, I learned, or at least from the analysis that Marcella has presented, that it's not also valid within the minimal supersymmetric standard model because of the extended, because the parameter space is squeezed to zero, actually. Right, so you may combine now the two ideas. So you need to have a very complicated models, and you may ask whether it is a simple framework. You may combine the two ideas, and you may have a baryogenesis through leptogenesis. So you may have a decaying particle now, decaying not in a baryon violating way, but in a lepton number violating decay. This was discussed in 1986, so I think the first and the last graph was included at that time. And this is a good idea to use, of course, the sphalerons to convert the lepton asymmetry to the baryon asymmetry. I will not go more on that. So I will only discuss possible models of leptogenesis just for reviewing this stuff. The first vanilla type leptogenesis, as mentioned before, was proposed by Fukuyama and Yanakita in 1986. And if you work it out with naive hierarchical neutrinos, you find that the lower mass scale, mass bound of the lightest of the heavy neutrinos, has to be heavier than 10 to 9 GeV. This is what is called the Davidson-Ibarra bound. And this was the case from 1986 up to 2004 or 2005. Okay, so, and of course, this idea has been, has the beautiful thing, of course, you have leptogenesis, but you nothing else. I mean, you may have light neutrino masses. You explain the lepton asymmetry, but there are no other possibilities, at least to trace or trace some aspects of this leptogenesis mechanism. At least you bet in a very higher symmetric framework like the talk we had before. So another scenario is this what's called the resonant leptogenesis. In this case, I will come back to that. You can evade that bound and other possibilities. You may have leptogenesis through Dirac in a kind of free-zine type of frameworks. But there are also other scenarios I'm going to talk here is the so-called non-thermal leptogenesis, which seem to work from Lazaridis and Saf in 1991. Affleck-Dinos spontaneous leptogenesis, or CPT violating leptogenesis, which I'm not going to touch here. So another point is that leptogenesis has a very, very complex flavor dynamics. You should not ignore that. This means not only B minus L, but 1/3 B minus the lepton number, the individual lepton numbers E, mu, and tau are preserved by sphalerons. So you have to generate the asymmetry using this conserved number and protect it. Okay, so there are two sources of flavor effects in this case. So the ones that enter in your Boltzmann equations. Okay, so the first one is the ones that do deal with such lepton-Yukawa couplings. And these were discussed, the reports of them discussed in 2006 in more great detail. And they may modify the baryon asymmetry by 1 order of magnitude, and around the scale, this Davidson-Ibarra bound, 10 to 9 GeV, where the mu and tau Yukawa couplings are going out of equilibrium or in quasi-equilibrium. So the heavy neutrino, however, there is another source which is very important, which gives a structure in this flavor space, which originates from the heavy neutrino Yukawa couplings. And this is an idea in 2004. It took 1 year to convince the referee in Physics Review Letters that these effects may modify the predictions of the baryon asymmetry by a huge factor 10 to the 6. Okay? And render, because of this, such lepton flavor violation in resonant leptogenesis models observable. Okay? That's the idea. So that means this scenario evades that problem we had before. Okay, so let me come to resonant, tri-resonant leptogenesis. This is a scenario, of course you may have seen these 3 graphs, and the important graphs that enhance the lepton asymmetry are the self-energy graphs. These are already known from 93, in 96 there were some papers on this, and of course this is reminiscent to a kind of K0 bar dynamics. And however, you can see that when you go closer and closer, the mass degeneration gets comparable to the widths of the heavy neutrino. Then you have to do something else. You have to include the width effects here in this intermediate state. So the perturbative results become finite. And this was done in 1997. And of course, you may say how you get inspired to that. I was inspired during my PhD times with a recent related paper, not on leptogenesis, but in collider physics from 1990.
during my PhD time. Right, so there are variants of resonant leptogenesis. One is the so-called soft resonant leptogenesis, which uses supersymmetry. Okay, uses the soft supersymmetric sources, which might be CP violating and may generate the non-degeneracies. The other is you may have this splitting of the heavy neutrinos through renormalization group equations. This is what's so-called radiative resonant leptogenesis. And of course, you have 1 year later, after 97, 98, Akhmetov, Rubakov, and Smirnov came up with, I think, very interesting and related mechanism, which is resonant leptogenesis by neutrino oscillations. Okay, so the field theory of resonant leptogenesis, I don't have much time to discuss all the technical details, but I like to give some glimpse on that. So this, in order to obtain the width effects, as already mentioned before, you need to get at least inspired or at least extend the so-called Lehmann-Szymanski-Zimmermann formalism for mixing and decay of heavy Majorana neutrinos. So you have this propagator, and this propagator of this particle alpha of one of the heavy neutrinos, you are truncating, if you like, with the inverse result propagator of the same particle, and then you multiply with the spinor. And in this way, you get an effective amplitude. So this is the, for the two neutrino mixing, which was discussed in 97. This was the propagator. So you have to take into account the chirality and all that stuff. And for the three neutrino mixing, of course, you have a more complicated structure. I'm not going to show here, but they are in the papers with Thomas Underwood in 2004. We discussed a little bit of that, or we used them in, with Frank Depis. And recently, we paid more greater detail in the dynamics that result from a tri-resonant scenario. So here I should say that this mechanism, or this way of getting effective coupling is used also in some collider phenomenology to discuss, for example, the case of unstable particles, but I'm not going to go there. But most of these formalisms for that is presented in 1997 and in 2004. So also I do not, so you get an effective amplitude. This H, and this H, you can see it has also absorptive parts for the self-energy and also absorptive parts from the vertices. This B is the vertices, this A is the self-energies, and you can see the mass difference here of the two heavy neutrinos get regularized from the absorptive part of the self-energies, which is this A beta beta. And this is the complex conjugate effective Yukawa coupling, and then it's very simple now. You can define lepton and gas symmetries, flavored asymmetries, by getting the difference of these Yukawa couplings. I will not, I will show how this works for two resonant particles. So if the mass is, so this is a plot, as you can see, you have two masses, Mn2 minus Mn1. So this is a parameter here that parameterizes the deviation from the mass degeneracy. And this is the CP asymmetry. The dotted line you see here, this is that time was 10 TeV, that's a plot from 97, is the perturbative calculation. You can see it explodes when the mass degeneracy becomes very, very small. But the result propagator, the one that I discussed before, you have a maximum which could be close to 1, and also it goes to 0 as the mass differences become closer, as expected from a Yatskok type invariant, from a CPT invariant. Okay, so you can have you can use also the scenario where the masses are in this region or in this region. So K0, K0 bar or B0 is in this region, and the D0, D0 bar system, for example, is on the other side of this. So experimentally, we have three good paradigms that go on both sides of this resonant region. So now the new idea now here is to not having two resonances, but you can have three in successive, in a successive order. So N2 is deviates by one width, and the second one by the width of the other. And you have a democratic structure to see what happens here. And you can see that, which is some approximate Z6 symmetry. The thing what you see here is that the asymmetries you get are slightly enhanced quite significantly. I would say 40%, 30%, compared to the fact if you are using the biresonant, if you assume only two resonants that you take each pair of two resonants, or the three resonant formula, which we have presented in 204 with Thomas Underwood. Right, so this gives further freedom to play with the baryon asymmetry. To do that, however, in a more sophisticated way, you need transport equations. These were first presented by Kolb and Wolfram. I will not go through all these technical details. That's what we like to say, that this is exactly what we adopted back in 204. And we calculate all these collision terms that needed for the Boltzmann equations. And these collision terms require to take into account not only the decays of the heavy neutrinos, but scatterings, delta Lhc. This one already known at that time. And this one as well, with the Higgs. But we needed to extend that and take into account delta Lhc. Not scatterings, flavor, lepton number conserving, but flavor violating scatterings as well, because I said the flavor dynamics is very complicated. You have to take this all into account, as well as gauge-mediated interactions. We have here a gauge particle. Okay, so you may get some order of magnitude estimate. That's what we did with Frank Depis. You can see here from the last formula here, you can have delta, you take delta order 1, and then you need a k of the order 1 million, so you can be almost k is a factor that parameterizes how far you are from out of equilibrium. So having k of 1 million, for example, you see that how close you are, you can be in equilibrium. This was vindicated now for another scenario, 10-3. We like to see how there is an attractor solution. We studied that. This was missing in the previous. So we have a good confirmation there is an attractor solution where the attractor solution fails, and so on. And the important point is here. I believe that's an important feature, that not 5. I measured, okay, anyway, 7 minutes, okay. Very exact. Yeah, 25, but I know when I started 40, okay, anyway, that's fine. That's fine, I guess. Right, so, okay, I missed the point now. So, right, so back in 205, you can see we confirmed the fact that was also discussed, that you can start with any baryon asymmetry, okay? You can have any framework, CPT value, you can, where the baryon asymmetry could have any value, positive or negative, and microscopically, the model which is presented here, you will get the same value in the freeze-out region, okay? So, and I believe that's a very interesting, very feature, that the baryon asymmetry does not depend on the how the universe was set before. It's just a prediction of your microscopic model, okay? Right, so I will go through that, not so, I mean, you need to do it in a more way. I think this was a paper we did in 2014. At that time, all they were very junior people, PhD students, and Dev was the first research fellow in Manchester. Now all of them have, of course, branched in different fields. So the point here is that the unified description, so with this formalism, which we like to advocate, there is a unified description of 3 physically distinct phenomena. The one is the resonant mixing between heavy neutrinos. The other is the coherent oscillation that you have to include. And there are different regulators here. There's a factor of 2. And, of course, you have to include decoherence effect. This is all that done in 214. The only thing we need to do it in this context. So let me go to a very important effect, which is to include also relativistic degrees of freedom, varying relativistic of freedom, not only the T, the Q, but the H effective T. By doing that, you will see that the baryon asymmetry versus the heavy neutrino mass, so there are parameterization for that. So H, the dotted line, is the constant, which usually people use. And you see if you take the running of the H effective of the entropy degrees of freedom, you may get different results. Actually, if you are very unlucky, you may get 0 for heavy neutrinos below the 100 GeV. So that for heavy neutrinos that are below 100 GeV, there are huge uncertainties according to that calculation. That's the new result. So whatever you see, at least from our point of perspective, for bounds and limits, combined limits and plots for heavy neutrinos, for sterile neutrinos much below 100 GeV, are suffering from these uncertainties, and in my view, should be taken with a great pinch of salt. I will not have time to discuss all the lepton flavor number violations, just to like to flash that you can have like sign dilepton signals. You can get constraints in this parameter space. And this is what I was saying before. You go very low in the heavy neutrino mass, then you need to do a different job, including the varying degrees of freedom. So the same thing for B nu. That's a very nice plot. You can see all the experiments, how they are constraining the parameter space, heavy neutrino mass versus light to heavy neutrino mixing. I will not have time to go through resonance evaluation at colliders, not about muon neutrinos double decay, which has no constraint in our models. Mu e gamma, I should say here the neutrinos you have in this minimal model are exactly the heavy neutrinos that produce mu to e gamma are the same heavy neutrinos you need for baryon asymmetry in the universe. Okay? That's a very important point here. So, for example, you can get some constraints here, 10 to minus 13 with 10 to minus 14. You get some constraints about this transition from muon to neutrino and electron, and I will come back to that. So the same thing from mu3. I don't have time to discuss all that. We did the calculation, the complete calculation, and also the coherent mu to E conversion. I think by Alonso and al. They also used another method for nuclear physics, but all these form factors were calculated before by us. This is an important project which is running in the Fermi Lab, I should say. And unfortunately, this paper is, it seems to be unaware about the cosmological relevance of their experiment. So let's begin to, that's my final part, the numerical estimates of these scenarios. So in this scenario, you more probably know the Minkowski, the seesaw mechanism. This is seesaw mechanism by Minkowski 77 and other people. And this is the Minkowski term. Okay, so in addition to that, so you may have, or you have radiative contributions you have to include. And this is the type 2. So they have an extra contribution next to the 3-level term, which is one particle irreducible. It's a non-local contribution, obviously. And there are these two terms. Some of them you can have models where you can put that to 0. And you have like the kind of variant of inverse seesaw model. This is not there, but you need to include these two graphs. Okay, and the other thing is you have these, all of them there. These heavy neutrinos cannot be very, very heavy. Sorry, not very, very different. Okay, they have to be nearly degenerate. That's the lesson you learn from that. So you should not forget the one loop contributions. And this is what I keep saying that. Of course, in some models, it's very small. So this is the plot we get. For the mu to E conversion, you may get something that could be prop at Fermilab, maybe. And, OK, so let me come to my conclusions. So I hope I have somehow convinced you that it's interesting to look that the resonant possession is an interesting mechanism to explain matter-antimatter asymmetry independent of the initial B number state of the early universe. Doesn't matter what the B state of the early universe is. So a complete, because we have to go to do a complete treatment. This is quite complicated. So you have we have discussed here tri-resonant and multi-resonant models offer new possibilities for model building, okay, which I have not discussed before. Varying relativistic degrees of freedom may modify significantly the transport equations to the to the extent that the baryon number, the Bow predictions for heavy neutrino masses below 100 GeV cannot be trusted. Okay, this is a strong statement. I understand that, but that's at least from the computing. I'm relying on my other collaborators to say this, to make this statement. If you like to have 10 to minus 13 and successful leptogenesis, this is what in 2014, you need at least 3 right-hand neutrinos and non-trivial flavor effects. Okay, this is something we are not considered in this tri-resonant scenario, but we are planning to do that. And finally, I like to optimistically say that that kind of heavy neutrinos might be able also to see signatures at the LHC or other colliders, future colliders, like FCC. Okay, thank you for your attention and your passion.
Thank you very much. First of all, it's a very nice talk. Questions?
Hi. So thank you for the nice talk. I just was wondering that since you showed these diagrams, which are basically 1 to 2 body decays, right? Which I just understand the diagrams.
Yeah, to 3, you mean?
Sorry?
Which diagrams?
The decays.
I don't know what you are talking. This one or
no. Much before.
The baryon, the transport equations.
Yes.
Okay. Ooh. This one?
Yeah, here and before this one, yeah.
Yes.
Yeah. So here, does the 1 to 3 body decays also affect, or they are phase suppressed?
Yeah, I mean there is a paper with other good in Physics Review D. You have to include 2 to 3 body decays and all that stuff. We have analyzed that, so it's a huge type of collision terms.
I see.
So, what was that? This is the second paper.
I see. Okay.
Addresses all that. This is these dots which I left here.
Okay. Thank you.
People use them. Yeah. But we like to do it better with covariance and flavor covariance.
So on your tri-resonant leptogenesis, how do you avoid the neutrino-less double beta decay constraints and more importantly, the corrections to the light neutrino masses?
Yeah, this is what I was discussing. I did not have time to talk about that because of the review and all that mixed audience which is here. When you have resonant leptogenesis models, you know that if you have one heavy neutrino, then you really have from the heavy neutrino constraint from neutrino-less double beta decay, which goes 1 over Mn and so on. So it has some suppression factor. So now in bi-resonant or tri-resonant, I think that's also a motivation for us. The nearly degeneracy of the heavy neutrinos at the very low scale, the scale that the lepton the neutrinos double beta decay takes place, is a kind of gym mechanism. There is a cancellation. So you get this contribution times the mass difference of these heavy neutrinos. You have an extra suppression factor, which is the mass difference of these heavy neutrinos divided by the heavy neutrino mass scale, which we are safe with that limit.
So in the case that you have 2 heavy neutrinos, usually that is justified with a slightly broken lepton number symmetry. So
yeah, in the case of the 2, or you have delta Mn over M. I mean, this is actually this point was raised it was discussed in this paper 207, well before other authors. Yeah. It was mentioned that. So if you have a 3, okay. You have to analyze it in a more detail. We have not done that. I agree with you.
Okay.
Yeah.
Thank you.
Thank you.
Okay, so the next speaker is Xiao Liu. And she will talk about the recent results of new physics searches from micromoon.
Good afternoon. Thank you for the opportunity for us to present the recent results from micromoon. I'm presenting here on behalf of the micromoon collaboration. The results will also have a focus on the new physics search. I'll start from the standard model of the neutrino from an experimental perspective. So in the past 2 decades, the oscillation experiments have painted us this picture from the new disappearance or new appearance oscillation experiments, showing the spectrum and give us to what we know as the standard model of the 3 neutrino paradigm. So all those oscillation measurements give us the matrix element of the PMS matrix. With the mixing angles indicated here, as well as the 2 mass splitting and 1 delta CP evaluation phase. In parallel with all those oscillation experiments, there was some anomaly creeping, especially in the short baseline. So that anomaly consists of the LSND, excess events in the anti-Nu-E channel, as well as the reactor anomaly, the gallium anomaly, as well as the mini-boom low-edge access. There are some recent results that is showing up in the reactor anomaly, which is kind of suppress this anomaly channel. But at the same time, the recent results actually presented in Neutrino 2022 also show some results from BEST that is confirming the gallium anomaly as well. So the picture is still kind of blurry, but what I will focus on today is to address one particular anomaly, which is the mini-boom low-energy access. Mini-boom is an experiment located at Fermilab when they measure the electron neutrino appearance at the short baseline located at the booster neutrino beamline. Just a few words about mini-boom low-energy access anomaly. Basically, what they're searching for is the electron neutrino-like events that it will show up in this electron access events in the electromagnetic shower. As you can see here, these data access events will show up at the low energy below roughly around 600 MeV, between 200 to 600 MeV. So this their background events here is show up in the different colors, but essentially you have 2 categories. One is those different shades of green that represent the final state has an electron, and that could come from the electron neutrino. And the other type is this brownish yellow color here, is the photon channel. So, so mini-boom low-energy access anomaly has been confirmed and consistent in the past years when they update their results, and it's about 4.8 sigma access in their Nu-E-like events at low energy. And as I already mentioned, in their histogram, there is a large photon background, and that is because the mini-boom detector, which is a Cranhawk detector here, does not have the capability to distinguish electrons from gammas. As you can see in this cartoon, here is different particle type, which will show up as in their detector, where both electrons and photons basically show up as a fuzzy ring here, that they are not able to distinguish them. The other thing I want to point out is in this box here, it's supposed to have protons, but mini-boom being a Cherenkov detector, their threshold for proton is very high, so they're not able to see the proton as well. So in order to address the mini-boom anomaly, understand what's the origin that caused that, this is motivated the proposal of the microboom experiment, which is the topic of my talk today. So the microboom experiment, since it's directly targeting on understanding of mini-boom low-energy access, it is located in the same neutrino beamline at Fermilab. As you can see here, this is the Fermilab booster neutrino beamline. That neutrino goes in this ring and then goes here, and then the neutrino beam is mostly muon neutrino dominant beam and goes in this direction. So in this location here is, and the blow up here as the drawing of the micromuon detector with this school bus size detector is located right upstream from the minimuon detector, which is located here. So essentially, micromuon is also on axis of Fermilab's boosted neutrino beamline around 500 meters baseline, and it has the same L over E as a short baseline oscillation experiment, same L over E as minimuon. Additionally, micromuon detector is also located off axis on the other neutrino beamline at Fermilab. It's called NUMI beamline, which later I will mention briefly as well. So the key point here is this micromuon is a new experiment with a different detector technology, which is a liquid argon TPC detector technology, about 85-ton active volume. And we want to use this new detector technology in order to address an anomaly that minimuon were not able to understand. So a few words about liquid argon TPC, this new technology. Essentially, so here shows a drawing showing the working principle of Lhc TPC detector, which I will not go into the details, but the takeaway here is it provides two type of detector signals, the scintillation light and the drift electrons. With those two types of signals, you're able to reconstruct and invent the original interactions in the detector and capable of have this 3D picture of the original interactions with a full pi solid angle. It produces so Lhc TPC detector produce high resolution images, and with the color, which is indicating the calorimetric information of the energy loss of the particle propagate in the detector. So with both the 3D event topology as well as the calorimetric information, we're able to understand or reconstruct the original interactions with the neutrino flavor and energy very well. So earlier I showed this picture of the Trunkov detector. Now it's a one-to-one correspondence of the Lhc TPC images that you can see that it produces those high-resolution pictures that show has the advantage of very nice particle identification capability. I will say a few more words on E-gamma separation in the later slides. But one thing that earlier I hinted for the minimuon detector is not able to see protons, but in micromuon we are able to see the proton as indicated in these very short tracks, and it's highly ionized, so the color is red in comparison with the minimum ionized particles. So since proposal, micromuon has been operation smoothly in the time period of 2015 to 2020 with 5 years of operation. It has collected the largest neutrino data set from a Lhc TPC detector. As indicated in this graph here, that there are 5 runs corresponds to this 5-year period. So since the neutrino data taken ended in 2020, afterwards we also have 2 post-operation runs that are dedicated for the Lhc TPC detector R&D since 2021. Analysis results that I will show in today's talk mostly use this first half of period data that corresponds to 7 × 10⁻20 POT. So earlier, I said micromuon was proposed in order to address the minimuon large access anomaly. But here, as the field evolved in the past decade, the micromuon's mission really should be divided into these 3 pillars, which consist of not only addressing the minimuon large access and as well as some other new physics searches, but also consist of the precision measurements of neutrino argon cross sections, as well as pioneering the R&D effort of using this advanced technology, liquid argon TPC. So we're able, in the past 5 years, we're able to transform those missions, the 3 pillar missions, into publications. As you were not able to see anything here, but just showcasing all our publications in this picture, color-coded with different years. So if you want to, if you are curious about all the detailed results, I encourage you to go to those links to see our 45 publications in the past 5 years, as well as the over 75 public notes that we're trying to communicate with the community with our progress. Before I dive into our primary analysis for addressing low-energy access, I want to first have a couple slides just talking about our precision measurements of the neutrino-argon cross-section program. So the prediction of the neutrino-argon interactions at low energy, so far we rely on the neutrino generators, but as you can see in this picture here, that at the low energy, the error bars is quite big, and those generators were not sufficiently verified from the experimental data. So Microbone's cross-section program aims to provide direct data constraint of the cross-section modeling, and those modelings are crucial for future new physics searches, as well as the oscillation experiments, such as the Dunes long baseline oscillation program. We're able to do that since with all the data that we collect, we have over 500,000 neutrino-argon interactions. So we have a big statistic in order to have smaller uncertainty, especially at this low energy. In this shaded area is where the microbone flux, neutrino flux is located. So in our cross-section program, is basically can divide it into two types of analysis. One is the inclusive cross-section measurements. The other is the exclusive cross-section measurements divided by the final states. So here I want to highlight two particular analyses. In the inclusive channel, the one I want to highlight is this nu-mu-cc, so charge current nu-mu interaction that includes all final states in the here, as shown here. So I want to point to you this recent publication that we have showing these double differential cross sections of the cis-inclusive measurements. Because, as I mentioned earlier, microbone is located on booster neutrino beamline, which is dominated by muon neutrinos. So here, that's why we're measuring the nu-mu-cc, which consists of over 95% of the muon neutrinos. And the inclusive charge current channel is also the key for any oscillation analysis. As you know, that normally for a nu-mu dominant beam, we measure nu-mu disappearance and nu-e appearance. It also offers the background race constraints. So this channel also providing the crucial constraints for new physics search, such as the IE search that I will present later for all final states. For the exclusive cross-section, the one channel I want to highlight here is the NC pi0, neutral current pi0 channel, which you can also see a publication that we're already submitted to PRD. Here shows an event display of an actual data event for neutral current candidate event with the pi0 decay in the final states that manifest as 2 photon showers. Why this channel is interesting? Because it's a neutral current, so it doesn't have the charge lepton in the final state, so you have less handles in order to find out the flavor and the energy. So it's not easy to reconstruct. And because of all those misreconstruction, this channel, especially with the photon or electromagnetic shower in the final state, it's very easy to mimic as your signals if you're looking for beyond standard model physics that also have either electrons or photons in the final states. So this measuring the cross-section of this channel provides an important constraint for any BSM searches that involve EM showers in the final states. As you can see here, which more details, again, you can find in this publication, that here is a cross-section measurement of the NC pi0 channel. I won't go through the details here, but here just to showcase all the other cross-section measurements in other channels that is happening in microbone, documented in this list of publication. So if you're interested, I encourage you to look through them. So now back to the main point of this talk, which is our recent results for the low-energy access analysis. This is our flagship analysis that, again, because we can do this to address the mini-boom anomaly is because the LRTPC capability to separate electrons from photons. So for those green events, which are the new E-like events, it will show up in our detector. It looks like in the top event display here. This is actual data, new ECC candidate. And those photon backgrounds will also show up such as this. And this event is a NC pi 0 that decay into 2 photons. So with LRTBC, we commonly have 2 handles to separate electrons from gamma. One handle is to see in this event topology whether we have a gap or not. So if you have a gap, that indicates that's a photon shower, a gap between the primary neutrino vertex and the beginning of the shower start. So if there is a gap, that means it's photon. If there isn't a gap, that means it's an electron shower. The other handle is a calorimetric handle, indicating the color again in these pictures. So for electrons, it's just one minimum ionized particles. For photons, often it will pair produce and produce the electron positron pairs. So at the beginning of the shower, it often corresponds to 2 minimum ionized particles. So use those calorimetric information, we can also separate the electrons from photon. So here is an overview of, with this capability of E-gamma separation, here is an overview of how we design our first round of LE analysis. Again, it has basically it has 2 categories of analysis. One is electron-like, the other is photon-like. A lot of details were also given by Andrew's talk, which is, in his slides on Monday's parallel session at 4 p.m., you can find all the details corresponds to this analysis. But the basic idea here is we want to, we have 2 types of search of the low energy access anomaly in the electron and photon channel, and we have independent analysis team as well as a procedure of the blind analysis scheme in order to minimize the analyzer bias. So diving in the electron type analysis, which the candidate is mostly coming from the electron neutrinos, which I also call it ELE search. So diving in this analysis, as I mentioned, there are 3 types of final state topology with the 3 independent analysis. But before we design our design the search, we first want to make sure that we have a signal model so that once we have the analysis available, we want to test our analysis whether it's sufficient to see if there is a anomaly appears, whether we can see that. So in order to do that, we have also developed this signal model, which is basically an empirical signal model, assuming if all the mini-boom low access anomaly events are caused by the electron neutrinos. More details of the signal model can be found in this public note. The basic idea is so the green here is the beam intrinsic electron neutrino, and if the mini-boom access exists, it will show up as this dashed red curve here. So back to our 3 independent analysis in ELE channel. So that divided into the final states with 1 electron, 1 proton, 1 electron, n proton, where n can be 0 or bigger than 1, bigger or equal to than 1. And then we also have the 1 electron with everything else, which is the inclusive channel, as shown in this cartoon showing the final state event topology. Not only with the different event final states, we also have different reconstruction techniques. As I mentioned, Microboom is pioneering the analysis techniques of the liquid argon TBC data. So we have developed different techniques such as using the deep learning, Pandora package, as well as the wire cell package, which I won't go into the details, but it's basically different analysis framework in order to reconstruct those different final state topology. There are advantage and disadvantage for each channel, so that's why they're all complementary. So for example, for the 1U 1 proton channel, it is the simplest event topology. That's why it has a lower background and it has more unambiguous energy reconstruction as well. But when you go to a higher energy, the event topology becomes more and more complicated. So I want to point out in this middle final states, This is the one electron with several protons, and this is identical as what miniboom is defined as their signal channel as well. So this can provide a direct comparison with miniboom. And then for the inclusive channel, it has this obvious advantage, which it's the most sensitive channel because it's the largest signal statistics, and it's also less model dependent, and it's mostly useful for doing when it's a wideband beam. Here showcased some event displays for each different final states, and we have separate publications documented all the details of those analyses, which I just highlight the efficiency and purity for different selections of each channels. The takeaway here is showing, so the bottom 4 plots are showing the reconstructed electron neutrino energy. That's the takeaway here is in the low energy access region, we basically do not, the data observation is basically consistent as what we predicted from our simulation in terms of the beam intrinsic nu E events. Here, just to summarize the previous 4 spectra into one plot showing the ELE search results. So again, in each bin here is the different corresponds to different channels, and here the red line is showing the empirical miniboom low energy access signal models. And as you can see, our data points are basically consistent as the predicted nu E events. That is either consistent or slight deficit even for each channels. So the result is showing our nu E candidates events are statistically consistent with the predicted background in the LE region, low energy region. And you might notice that in this one particular channel, which is the final state has no protons. So in this channel, the data has slight excess. But I want to point out this is the least sensitive channel, and blue region here is showing that it's a channel of mostly background dominated. The hypothesis that nu E events are fully responsible for the medium miniboom low energy access is rejected with the 97% confidence level. And in particular, the inclusive analysis has the most sensitive results, is showing larger than 3 sigma rejection in the inclusive channel. So earlier, a few decades ago, when micron was just born, the motivation was to search for these EV-level stereo neutrinos. However, as the field is evolving, this vanilla 3+1 stereo neutrino model is less and less popular. But nevertheless, it's still a good benchmark model for us to test our sensitivity and also test against our results. So we did the exercise using our ELE analysis. So here is our example of our inclusive analysis channel with the reconstructed neutrino energy. And then we reinterpret this analysis to see whether this is, and then did a fit in 3 channels with the nu mu disappearance, nu E appearance, and nu E disappearance. This 3-channel fit will be able to see the exclusion curve to show in the 3+1 parameter space in this mixing angle and the delta M41. So I want to point out this red line here is our result using this inclusive analysis with a 95% confidence level. And in the future, we also want to include the NUMI data. As I mentioned earlier, micron has both BMB and NUMI data, which will improve our 3+1 exclusion curve pushing to the left, corresponding to the sensitivity corresponds to this purple line. Beyond this inclusive analysis, we also have some other in the exclusive channel in order to have this 3+1 test in our data results. So I just told you about the effort on the ELE search in the nu E channel. In parallel, we also have the photon LE search. In particular, I want to emphasize here, we start with a particular photon channel, which corresponds to this delta radiative decay. So just to remind you from the miniboom, this mustard color corresponds to neutral current a data resonance that goes into a nucleon and a photon. So if you increase this background by a factor of 3, that basically match to the shape of this access in low-energy access in mini-boom. This is why this is the first channel we want to start to look for, see whether there's access channel in this access events in this particular channel. So this is showing the simple Feynman diagram that in this delta decay, radiative decay, it can this n, big N here can be either protons or neutrons. So that means in our data will manifest as final states with either 1 photon, 0 proton, where N is the neutron, or 1 photon, 1 proton, where N is the proton. So following this strategy, we have the two search in these two final states, and this is showing our results. Because this event rate is very rare, so it's a background dominant channel, so we use the 2 photon channel in order to provide the constraint. And in its right column here is showing the results after the constraint. To summarize the results, we do not see data access in this channel, and it disfavor the NC delta that is induced by the single photon as the sole source for mini-boom access. We also set the best limit in this channel has a 50-fold improvement from the previous T2K experiment. So so where we are now, the first LE results search in the nu E channel and the NC delta channel, we do not see access. But this means the origin of the mini-boom access is still not known, and we have not ruled out the possibility of access in all photon-like channels. So the next immediate question we ask is, do we see access in all photon-like channel? So currently we have the ongoing analysis that is investigating searching for the access events in the inclusive photon channel that could incorporate in all those other particular physics process. And in this public note, we have documented our effort on this selection. Depends on whether we see access in the inclusive photon channels and answer those questions. You can imagine that we design our follow-up investigation on the mini-boom low-energy access in a more and more model-dependent search, as shown in these final columns here, that is targeted on different beyond standard model physics searches. So I don't have time to go through the details of those searches. I will encourage you to look at my colleague Pavel's talk on Monday at 4:20 for the exciting progress that we have for beyond standard model searches in microboom. The two results I want to highlight in particular is this heavy neutral lepton search results, as well as the Higgs portal scalar results, which are published in PRD and PRL. This is my last slide. Just want to show the exciting prospects in the future for the BSM searches in microboom using the nanoseconds timing. So earlier I always showed about the LRTPC particle ID capabilities, but what is often not mentioned too much is about the timing of using those LRTPC detectors. Recently we have made some breakthrough on having achieving nanoseconds timing resolution. So you can imagine for any long-lived particles which are produced at the beam target, which will fly slower than the nearly massless neutrinos will arrive at the detector later. So for the booster neutrino beamline, we have this bunch structure, and we are able to use this bunch structure to achieve background suppression, especially for the neutrino background. So the prospects of BSM searches in microboom and the future LRTPC-based neutrino experiments is very good. So here's my summary. So in this talk, I've shown you our first LE results, as well as some continuous effort on investigating the low-energy access from mini-boom. And I also show some, highlight some results from the cross-section measurements, and microboom will be continuously providing our findings and publish in those efforts. Thank you.
Thank you very much for such an informative talk. That's very good. Any questions?
Have you tried dumbing down your detector so much that it looks like mini-boon? That is not distinguish between electrons and photons at all, and just try to do a completely inclusive analysis to see whether you even reproduce the excess at that level?
Well, it is a different experiment. So whatever suggest.
No, but you have more. You can do things that they can't do, but you can just switch off all these features, right? You should be able to more or less reproduce their analysis. Just look for some electromagnetic signal and in the energy bin without trying at all to distinguish, to figure out whether this is an electron or a photon or two photons or whatever.
Yes. So basically, at the beginning, we designed analysis in order to just look for excess in the EM shower. We basically place our E-gamma separation cutter towards the very end of the analysis. And if you reverse this E-gamma separation cut, and then, so we haven't have the published results on that, but in principle, yes, we can reverse the cut and see whether we have access there. And then, but our results so far is showing in the two channels that we searched, we cannot reproduce mini-boon access.
Well, my first question was exactly his questions. Why? Because we still don't know if the excess at mini-boon was there in the first place, and that was, I thought, that first question that Microboon wanted to answer, but so far that is not answered because
so far we have not seen the access.
You haven't done the inclusive photon analysis.
Yeah.
But could you show the neutrino appearance analysis, the electron appearance analysis, the different plots in the different final states that you analyze? No, the previous one. So in the 1E NP that is the most similar to so do you worry at all that your data doesn't seem to resemble the background or the expected background at all? Then look at that, look at the green and look at your data. So then it looks quite different, right? Strikingly different.
So you mean the data here? Yeah.
Yeah.
So currently this analysis is still statistically limited. And so one thing that I didn't mention too much is a subtlety that we use our new mu channel to constrain our new yield analysis. So there are, first of all, a lot of uncertainty, especially at the low energy, for the generator to predict the cross-section. But we use our data constraint to tune the predicted backgrounds. So,
but then you use this statistically limited to put strong constraints on the models. That I don't understand.
We use this, so the strong constraint, the 3/3 sigma exclusion, is the inclusive analysis, which are not statistically competent.
The inclusive analysis doesn't look like a shift in the, look at there seems to be a shift in the energy reconstruction, but anyway, so that is my view of it. Looks quite strange.
Yeah, so...
Anyway, so I just worry about, I look at these figures and I worry a little bit about the comparison of your data and background.
Yeah, so statistically, we can still claim it's compatible. And we are going to use our full data set. So this is, remember, half of the data set.
That's why I think, okay.
Yes.
Last question. To follow up on that, these two right plots are correlated, right? All the events in the middle right are in the right one, yeah?
Yes, so there are some overlapping events. In principle, this channel should include all the events here, but because we're using, it's a completely independent analysis and different techniques, so there are some overlap between the two.
Okay, because there are some similar dips in both, but those are probably similar events.
Yeah.
On the slide 17 on that limit plot, it's great to see exclusion plots now in the new recent results. So I guess it really means a lot of just, this simplified model has been excluded except for some small sliver of that blue place next to the red line.
Yeah, the blue place here is the LSND allowed region. And the red line here, yes, basically you can claim So there is some subtlety here. If you look at the minimal exclusion plots, they have the fits only in the new E appearance channel. And here we have more fit parameters that considering all three channels. We basically allow the new E appearance and new E disappearance. So that curve is somewhat different from the exclusion curve from miniboom. So that's that subtlety.
Could you comment in that sense the difference between green and red here?
The green here is so the red is allow new E can disappear and new E can appear. So you have the mix. You have two more mixing angles. For the green here is artificially you only allow new E to appear.
So red is
Red should be more correct. Yeah, but miniboom is using the green.
And going up on this plot is even smaller sterile neutrino masses, right? Even
Sorry?
larger mass splitting. If you go up on that plot, that potentially goes to smaller sterile neutrino masses. Because that's a mass splitting, right?
A bigger mass.
Okay.
So this thing is bigger. And the last speaker of the session is Alan Faraji, and we'll talk about the spinor vector duality and the swampland.
Well, thank you very much for the invitation to speak. It's a pleasure to be back. And what I'll talk about today is about an alternative approach to the question of the relation between string theory and its effective field theory limits, which is, so the swampland program can be viewed as a bottom-up approach to this question, whereas what I'll describe today can be viewed as a top-down approach. So this work has been done. So in particular, I will talk about spinor vector duality, which was initially observed in a paper with Kostas Kounas and John Rizos. And does it work? Right, so the paper with Kostas Kounas and John Rizos, where we first observed the spinor vector duality, and I'll discuss work that we've been doing in the last 2 years about seeing the imprint of this spinor vector duality in the effective field theory limit of the quantifications, string quantifications. Then I'll discuss, so I think depending whether time will allow, I'll discuss some other kind of symmetries that you can see from the worldsheet point of view in the effective field theory limit of string quantification. So the question that the swampland program asks is, when does an effective field theory model of quantum gravity have an embedding in ultraviolet complete string theory? So as I said, it can be viewed as a bottom-up approach. String theory, the feature that string theory has is that it has a massive spectrum, and typically the way this massive spectrum is exhibited is in different forms of dualities in which you exchange massless modes or massless states with massive states, which you cannot see in the effective field theory limit. You don't see it in the effective field limit a priori. So the approach that I will describe today is how do the string dualities and symmetries constrain the low energy effective field theory limit. And the celebrated example of this over the years has been mirror symmetry. So mirror symmetry has been initially observed in worldsheet string quantifications, but opened up a whole new field in pure mathematics that essentially dominated pure mathematics for a couple of decades. And it was a very, very profound, had very, very profound implications in terms of the effective field theory limit, in terms of Calabi-Yau quantifications. And what I will describe today is a similar kind of symmetry. In fact, it's an extension of mirror symmetry, which is this spinor vector duality. And then, from the worldsheet point of view, these are just two mere examples. There's a very rich symmetry structure that I sort of dub as modular maps. And one particular example that, if I have time, I will discuss is a map between SUSY and non-SUSY string vacua and the associated model building. So just to put it into context, especially in this forum, this conference, that's primarily interested in say, more phenomenological questions, to my mind, whether SUSY is realized at the Lhc scale is a secondary question. It could be realized above the Lhc scale, and but what we observed with following LHC, the observation of the Higgs at 125 GeV, it is compatible with supersymmetry. It is the mechanism, the electroic symmetry breaking mechanism is perturbative. It looks to be perturbative. What we observe at the LHC, the Higgs that we see appears to be a fundamental scalar particle rather than composite. And to me, that's really the strong what we have learned with. So we should take from the LHC. And as I said, especially over the last year, that if the Higgs turns out to be composite, I will abandon this field. I will abandon string theory. I will choose to do something else because it's very difficult to accommodate the composite Higgs in quantum field theory models, let alone in string theory models. So I think this is really the message. And the standard model, since it's been invented or sort of constructed in the early 70s, begs to be unified. I mean, its raison d'etre is to be unified. I mean, we heard from Dimitri about the flipped SU5. And so this fermionic Z2 constituted orbifold, of which the flipped SU5 is one example, it gives you a framework in which you can study the phenomenology of the standard model and unification in the context of a theory that unified gravity with the gauge interactions. Because I think that many of the questions that we would like to ask, like fermion massing and so forth, or say the flavor structure, we heard from Peter Linus about a top-down approach to the flavor structure, cannot be addressed until you unify the gauge interaction with the standard model. So the fermionic Z2 constituted orbifold that Gary Shu calls the Z2 orbifold the harmonic oscillator of string quantifications, has been sort of, they provide you a laboratory in which you can ask many sort of phenomenological questions and try to answer them. And so this has been pursued since the late 80s. I mean, it led to the first, say, model that reproduces solely the spectrum of the minimal supersymmetric standard model in the low energy effective field theory. I mean, a prediction for the top quark mass several years before the top quark was discovered at the right order. And then many other questions. In the past few years, we've been sort of looking at large classes of models with work that started with Kunas and Rizos, and then in the last couple of years, in the last few years, with my students at Liverpool, Ben Percival and Victor Matthias. And it also gives you a framework to study cosmological questions that's been pursued by the Paris group. So that, again, so what the work that I've been pursuing is the context of the heterotic string, but you can study the important message is not the heterotic string. The important message is that the structure that is relevant for the phenological data that we would like to describe is this structure of the Z2 cos 2 orbifold. So you can study this structure from using different other limits of the other limits of the perturbative string theories, as well as 11-dimensional gravity. And in the last few years, with my student in Liverpool and as well as other people, we have started to looking at this structure in the context of non-supersymmetric string vacua, and in particular, non-supersymmetric string vacua that are tachyonic in 10 dimensions, but are tachyon-free in 4 dimensions. And this have not been looked at since the mid-80s, when they've been sort of observed. We heard a talk this week by Carlo Angelantoni about some of the features of these quantifications. Right, so just a little bit on the fermionic construction. So all the worldsheet degrees of freedom are represented in terms of free fermions propagating a string worldsheet. Here we have 5 complex fermions corresponding to the GATT group, 8 complex fermions corresponding to the Eden sector gauge groups, 3 complex fermions corresponding to 3 U1 symmetries, and then you have 12 real fermions on the left and 12 real fermions on the right that correspond to the compactified 6-dimensional coordinates, and you have 8 real fermions that correspond to the Ramon-Schwarz fermions. Now, when you transport these fermions around the non-contractible loops of the torus, they pick up a phase. If, for example, if alpha is equal to 1, so then the fermions will be periodic. And then you can construct a partition function and constrain the imposed model invariance and constrain the allowed transformations. And so models in this formalism are constructed in terms of the set of basis vectors and the one-loop geosurf phases in the partition function. So here, in the last, so since 2003, with Rizos and with Kunas and Rizos, we developed a systematic way to classify large spaces of vacua. Here we fix the set of basis vectors. The notation here denotes the fermions that are periodic on the worldsheet, so they have a boundary condition equal to 1. And here, the second basis vector that I have here has 8 real periodic fermions on the left side of the heterotic string. This is the basis vector that generates space-time supersymmetry, and I refer to it as a modular map. So whenever you add this basis vector to any other sector in the theory, it will produce the superpartners. So I refer to this form of vector as a modular map. And then we have, here we have basis vectors that correspond to shifts in the internal coordinates. We have two basis vectors that correspond to the Z2 cos 2 orbifold. And then you can add basis vectors that breaks the SO10 symmetry to some subgroup. Now, the way that the models are enumerated is by varying the phases in the one-loop partition function. So here, for example, for this set of basis vectors, where these are Petit-Salam models, these correspond, so you have imposing modular invariance, you have 66 independent coefficients, so you have 2 to the 66 distinct vacua with different spectra, so it's about 10 to the maybe 10 to the 15 different vacua with different spectra and so forth. And that's the way we classify large, we look at the properties of large spaces of vacua, and in particular Ben Percival over the past few years, he adopted a class of artificial intelligence programs which are called satisfiability modular theories. So before using this methodology that he adapted in this program, the running time, say, of 10 to the 11 vacua could be 11 weeks, but using these artificial intelligence programs reduces the running time by 3 orders of magnitude. So let me go to the issue of spinor vector duality. So let's start with the case of mirror symmetry. So I enhance the SO10 symmetry to E6 by adding a basis vector that will give me the 16 plus 16 bar that enhance the 45 to E6. The mirror symmetry, what it does, it exchanges the Euler characteristic with its inverse. So it exchanges the number of 27 with 27 bar, and it corresponds to a transformation in the moduli of the internal manifold. So it exchanges the complex and Kähler structure moduli. Or in terms of toroidal orbifold, it will exchange the metric and the antisymmetric tensor. So it's a map in the internal moduli of the toroidal string. And Waffer-Witten in 1994 described the mirror transformation in terms of discrete symmetry that in the fermionic language I can realize as the discrete torsion between the two Z2 twists. So let me now describe the spinor vector duality. This was initially observed in a paper in work with John Rizos and Kostas Kounas. So it's duality under exchange of the total number of spinors of the SO10 grad group and the total number of vectors. And we initially observed this symmetry just by counting. So counting the number of vacua with 2 spinors or with 2 anti-spinors, or with 1 spinor and 1 anti-spinor. So you just count the total number of models, and you see that this is exactly the same. This is a 10-digit integer. So you add them up, and you see it's exactly the same as the total number of models with 2 vectorials. So that's how we initially sort of conjectured that there is this duality. And so the duality says that for every model with a number of 16 plus 16 bar and a number of 10 of SO10, there is this another model in which they are interchanged. And this reflects, this is reflected in discrete transformation of the GSO phases. So there is an invariance under exchange of the total number of 16 and 16 bar and the total number of vectors. This is a density plot that again reflects this duality. It's symmetric under exchange of rows and columns, so this is in a much larger space of vacua. And the origin of this symmetry is very simple to understand if you consider the enhancement to E6. So in the case of E6, the 27 is composed of a 16 of SO10 plus 10 plus 1, and the 27 bar is composed of 16 bar plus 10 plus 1. So if you count the total number of 16 plus 16 bar, it's equal to the total number of vectorials. So E6, the case of E6, is a self-dual under this spinor vector duality. So the statement is that when you break the E6 symmetry, or when you break the 2,2 worldsheet supersymmetry to 2,0, there is a remnant of this discrete symmetry, which is this spinor vector duality. And one notable point here is that there are self-dual models along this diagonal that have the same number of 16 and 16 bar and the same number of vectorials without enhancement to E6. Let me describe this in terms of orbifold. So we can start with a torotic E8 cross E8 in 4 dimensions. So we have here an internal lattice, and we apply 2Z2 transformation. One is a Wilson line that breaks the E8 cross E8 to R16 cross R16, and the second is a Z2 twist in the internal compact space. And we have here a single space twisting, so n equal 4 is broken to n equal 2, and we discuss the spinor vector duality in terms of SO12 rather than SO10. And instead of E6, we have E7, just because we are looking at a single Z2. So we construct the partition function. So this is the partition function. And the partition function will have in it 2 orbits, so the two orbits in the partition function. and there is a discrete torsion here, epsilon, and we'll have massless states. So massless states will correspond to, will attach themselves to the massless modes of the internal torus, and there is a massive spectrum. So there is a discrete torsion that can take the values plus minus 1. So you analyze the partition function, and you have these two projectors in terms of the discrete torsion. You see that for epsilon equal to plus 1, the massless mode of the internal torus will attach themselves to the vectorial state, whereas for the spinoidal state, they will be massive. So in this case will give you a massless vectorial, whereas for the opposite choice of the discrete torsion, the massive mode will be attached to the vectorial, and the massless mode will be attached to the spinoidal. So this is the reflection or the inducement of the spin-of-vector duality in terms of the discrete torsion. Now, this opens up a whole new world of analyzing this spin-of-vector duality in the effective field theory limit, and this is what we've been pursuing with Stefan Gut-Nibling and my student in Liverpool, Martin Hurtado Heredia. So essentially, we looked at orbifolds. So we took orbifolds that exhibited this spin-of-vector duality, and we resolved the resolution, and we showed that there is a remnant of this spin-of-vector duality in the effective field theory limit construction. So we looked in 5 and 6 dimensions, and from the point of view of the effective field theory limit, there's no reason the compactification are not constrained. So in the same way that you don't expect the mirror symmetry from the effective field theory limit point of view, the world of 2,0 compactification, which is where we expect phenomenology to be relevant, is not constrained. There's no reason to think that you cannot have examples that are not spin-of-vector dual. What you learn from the worldsheet theory, from the worldsheet, that the effective field theory will be highly constrained because you have this spin-of-vector duality. So, as I said before, Waffer-Witten showed that you can realize this discrete torsion, the mirror symmetry in terms of discrete torsion in the Z2 equal to orbifold, and you can ask the same question in the case of the spin-of-vector duality. You can look for the imprint of the worldsheet symmetries in the effective field theory limits. Right. So you can. So since I won't have enough time to describe everything that I wanted, you can just realize this spin-of-vector duality in terms of a modular map. So that it's just constructing a different basis, and you then realize the spin-of-vector duality as a modular map, and then you can extend this picture to compactifications with interacting internal CFT, essentially to more general Calabi-Yars, and that was done with Panos Athanasopoulos and Doron Gepner. Right, so this picture of modular maps is especially rich in 2 dimensions. In 2 dimensions, there's a field called monstrous moonshine, or the space of symmetries in 2 dimensions is very rich. So you can study this richness so in the context of this construction. So I'll skip this. Another topic that we have been pursuing so with my students in Liverpool in the last, this is essentially since COVID sort of began. So over the COVID period, you can induce a similar modular map that, so this is a SUSY generator that I described before, by, so this map, adding here 4 periodic worldsheet fermions in the Eden sector essentially takes you to a vacuum which is in 10 dimensions is tachyonic. So it's a compactification of a vacuum in 10 dimensions which is tachyonic, but then you can project out the tachyons in the 4-dimensional model. And then you have a map that you can take any model that is supersymmetric say, in 4 dimensions, and you can map it to a vacuum which is non-supersymmetric. So it's another application where you can study the imprint of worldsheet symmetries in the effective field theory limit and their implications for phenomenology. And so we've been doing this sort of classification of large spaces of vacuum, and in this context, the interesting question that we've sort of looked at is essentially the distribution of the vacuum energy and the distribution of bosonic, massless bosonic versus fermionic states. So looking for cases where you have equal number of bosonic and fermionic states. So in my last minute, let me describe another phenomenological implication that might be of more interest to this audience. This is the case of building Z prime, so string-derived Z prime models that can, where the, if you look at it from the point of view of the worldsheet construction, of this worldsheet string compactification string models, typically the U1 that people are discussing in, say, in the string-inspired literature is anomalous, so it cannot remain unbroken down to low scale. So what we did with John Rizos, we constructed a string-derived model where this U1 is anomaly free, and the way we did it was we extracted, we fished out a model which is self-dual under the spinor vector duality, and then in that case, the spectrum, although it does not sit in complete E6 representation, it doesn't follow E6 representation, it still sits in complete E6 representation, and the U1 is anomaly free, so it can remain unbroken down to low scale, and then this gives, so it can remain down to unbroken to low scale, and I think that it's very well motivated from a phenomenological point of view, because so we studied it in the context of, initially in the context of sterile neutrinos, and if you look from the point of view of string theory, the sterile neutrinos will typically, if you look at string construction, will typically have a mass of the order of the Planck scale. There's no reason for them to remain light if they're not protected by some symmetry. So the idea here is that the U1 under which the chiral is broken at scales that are relatively light, and then they can only obtain their masses once the U1 is broken. So this is motivation for the U1 to remain unbroken down to low scale from a phonological point of view, and you can extend the argument to the from the point of view of supersymmetric constructions to the Higgs doublet, namely the mu parameter it can only be generated in these models once you break the U1 symmetry. So this explains or can explain the existence of light Higgs within these constructions. Okay, thank you. So I'll put.
Okay. Thank you a lot for an interesting talk and to restrain to the time, which is good. Any questions?
Thank you, Alan, for the very nice talk. Could you go back, please, to the slide where you have the non-tachyonic theories, please? This one. The next one. Yeah, this one. Yeah, this one. I have two questions. The first one is there is this S tilde basis vector in your theory, there is this S tilde, if I can see well, vector in your theory, which couples the RNS fermions, gives the same boundary condition to right-moving fermions.
Sorry?
The RNS fermions on the left are coupled to the right-moving fermions from the gauge bundle. And by giving them the same boundary conditions, you here, if I understand correctly, you do not have a spontaneous break. You cannot have a spontaneous breaking of supersymmetry. I understand correct? Okay. And if you can go also to the next slide. No, the next one is the one with the plot. Yeah, this one. Yeah. So one question I have here is that in these models, you are sitting at a fermionic point, right? What? You are sitting at a fermionic point in moduli space, right? Yeah. So in this case, I presume your vacuum energy is going to be very big.
Of the order of the Planck scale.
Of the order of the Planck scale. So even if you set, let's say, an equal number of masses, bosons, and fermions, it's still large. Okay. Thanks.
Sorry?
In the landscape of models that you consider, do you consider models in which the fermions cannot be complexified? In other words, that there are Ising models?
You mean the asymmetric one?
Yes.
I mean, so that's something that we developed in our last paper. Essentially, we extended the classification method. You know that from the model in the 80s, we had the asymmetric. They were asymmetric, and they have very interesting chronological implications. The systematic classification method that we developed with Kostas and John always used symmetric boundary conditions. But in the last paper with my students, we adapted it, started to adapt it to asymmetric boundary conditions.
Yeah, because in that case, the models cannot be described as Z2 cross Z2 or will not be able to be described as Z2 cross Z2 herbifolds because you have. Bosonized, I mean, they cannot be bosonized.
No, but the asymmetric boundary conditions we consider correspond to asymmetric shifts. The twists are still symmetric. And so they correspond to sort of default. I mean, you mod out moduli. They mod out the moduli.
Thank you, Alon, for this nice review. As an ignorant on this subject, you're going to have exotic vector states in your spectra or not? I mean, exotic means non-standard model type things. Vector. I mean, my question goes back to the talk we heard from Miriam yesterday, that in her compactification, she didn't have exotic vector states. So that's my question. Vector-like, yeah. That's right. Yeah.
So in this construction, with John and Kostas, we constructed what we call exophobic.
Yes. Right. Mm-hmm.
All the functions are state attach themselves to a set of SO10 sequences in the model. So you give a vector to this set of SO10 sequences, then all of them will get a mass of the order of this line size within scale. So that model essentially
Okay. Okay. Thank you. Thank you.
So, hi, about the excursion, buses will leave from here at 2:30, okay? So it is strongly recommended to wear your mask inside the buses. And okay, that's it, lunchtime.
So now let's take this.